Welcome aboard, my dear JEE warriors. This is your Captain Shreyas on the JEE Physics English channel, and we are here today to start the next chapter of magnetic effects of current. Just 1 second. Yes, yeah, I'm audible. Great. So today we are going to start magnetic effects of current, where we will discuss how magnetic field is produced. In the previous lecture, we had already seen how exactly magnetic field produces forces and effects on current carrying wires and moving charges. That was your Lorentz force and also your forces on current carrying wires, ILB, QV cross B. Then we also defined what was magnetic moment, figured out the torque acting on it, also studied the motor working principle and also the potential energy of a magnetic dipole. And we ended the class with gyromagnetic ratio. So if you want all of those, make sure you're checking out this particular lecture of magnetic field and Lorentz force. I'm actually kind of following the H.C. Verma order of completing this chapter. H.C. Verma sir, starts with the concept of effects first, and then he starts with the concept of the sources of the magnetic field. So today we are going to learn about Biot-Savart's law, and also we are going to learn about Ampere's law. We're going to see different geometries like straight wires, curved wires, or even loops, and then solenoids, toroids, and also even sheets. So that is what we are going to focus today. Like always, we'll start with the basics, slowly scale up. I'll make you solve questions, make you ready for JEE. So this is a proper concept building class with proper application. Obviously questions are there, and in detailed theory right from zero, right from scratch. So welcome aboard. Hi Atman, hi Arpan, hi Rasika, hi Sanju, good evening, hi Faizan. Okay, shuru se class karna hai to you can do one thing. You can either join the Lakshya batch or you can even check out our lectures which you are conducting. But these lectures, remember, are really good obviously, but if you want assignments, test series, DPPs and a systematic regular flow, then I would suggest you to join the Lakshya batch. Else, if you are already enrolled and you just want to know about the concepts, then these lectures are a gold mine. That's what I can suggest. Okay, great. How long will this class be? I don't know, maybe 3 hours. Yeah, it's not very big, but it's not very short either. Cool. So let's begin with the lecture, and let's start with a very interesting concept. Now let me tell you, the first few minutes of this class might actually blow your mind, and if it blows your mind, really good. And if you get confused, please don't blame me. You can directly skip to the next part after those 5 minutes, because I am literally going to reveal you the truth. And not many books, not many teachers, not many people really explain magnetic field, what it is really, and people learn about it later on, eventually, maybe not even in JEE, maybe in MSc, or sometimes in JEE Advanced, and sometimes in some nice Olympiad question. But I will start with that, because people just think that something think about magnetic field as something which is very different from electric field. But I have mentioned this before also in my previous classes, that electromagnetism is actually a unified force. They are not two different forces. But what does it really mean? So let's understand that. Okay, are you ready for it? Music, hi, MGW, welcome. Yep. So I hope you are ready to take in whatever I am going to say. All right. So be careful. It's going to be very interesting, but it is also I know very, very non-intuitive. It's not something which you can digest so easily. Okay. Now we understand electric field is produced by charges. You say magnetic field is produced by currents, but current at the end of the day is moving charges. So that brings me to my next question. Can charges really produce electric field as well as magnetic field? And if so, what is so different in magnetic field? Because I thought only charges can produce electric field. How is it that they suddenly produce magnetic field? And then some people say Actually, magnetism is just, same as electricity, is just a different way of looking at it. What do I mean by it? I will answer that. Look at this particular person. He is in a spaceship, alright? And for us right now, the spaceship might be moving, not moving, I don't care. I am sitting within that spaceship. So my observer, the frame of reference, is the spaceship itself. So here I will clearly mention that my observer or the frame of reference is that particular spaceship. Alright, just take it. Now this is our observer. Let's take in two charges. Okay, let's take in two charges. Let's say one charge is here and another charge is here. Let's assume both of them for now are positive in nature. Both of them are now positive in nature. This was initially, let's say at t is equal to 0 initially. Some time passes by, maybe a minute or 2 minutes or 3 minutes or 5 minutes. What happens after 2 or 3 minutes or 5 minutes? These charges will obviously repel and they might have to move apart, and they will start applying those repulsive forces and they will eventually reach some point, maybe over here, maybe somewhere over here. Like this charge has moved this much, this charge has moved so much, and it has reached here. Let's assume the dark blue is after example 5 minutes. I can take 2 minutes, 3 minutes. This is just for your understanding purposes. So I know that if there is a spaceship, let's take it inertial frame always. Okay, otherwise pseudo forces will come. So it's an inertial spaceship. We know that if these kind of charges are kept at certain distance, and if I wait for 5 minutes, they will have to move some amount. Okay, and that amount will naturally be fixed. No matter which spaceship you take, no matter which observer, person you take as the role of the observer, because those two charges, whether it is 2 coulomb, 3 coulomb, I don't care, some charges, those type charges will move so much in that much time. If I change the charge, it will move different. If I change the initial distance, it will move differently. If I change the time, obviously it will move differently. So for a particular charge, for a particular initial separation, for that time period, it will move by some amount. Agree with this? Very simple to visualize. They will just repel. Now, let's visualize what could be happening for an observer who is outside. Alright, so this is an observer who is outside that spaceship, and remember this particular spaceship is now going to be in motion, and let's assume that this particular spaceship was in motion in this particular direction. This is the motion of the spaceship, as seen by an outside observer. And who is our outside observer? I've just shown it over here. I'll just again mention this. This is our outside observer. He is seeing that spaceship is moving like this. His friend is inside the spaceship and making his independent observations. Okay, till this point, everybody clear? Great. Now observe this carefully. Initially, for this particular person at t is equal to 0, these two charges were here. We wait for 5 minutes. This is at t is equal to 5 minutes. And we expect the charges to have moved so much here and so much here. That is what we expect it to move, and that is what should happen, right? That is what happened over here. Initially, it was here. After 5 minutes, they have moved apart by some amount. So, as this observer is making his independent observations and he sees those charges moving apart, one can think, oh sir, I got to know what is happening. This charge is moving like this, and this charge is moving like this. for an observer outside. For an observer outside. Great. Now let us ask him. Let us ask him, does he really see this or does he see something different? Okay, that is the funny part. If you ask this observer, does he see this motion and this motion of these charges? He will say, no, I did not see that. He will not say that I exactly saw these kind of motions. That is the funny part. He will say, I saw slightly different motions, number one. Number two, he will say that these charges did not actually move so much. They have moved little bit differently. He won't say that these charges are here after 5 minutes. He will say they have moved differently. You will start scratching your head. Why is it so? So here the concept of relativity comes, which Einstein told. And it so happens that whenever you have a moving frame of reference, time slows down. So whenever you have a moving relative frame, so you have this particular moving frame. This is moving spaceship. Moving spaceship. Yeah. So what happens is, my dear warriors, for this person inside, these charges should have moved so much and reached over here. But what this person will actually say, that actually these charges have only moved this much and this much, slightly less. There are these concepts of length contraction, time dilation, which happens in relativity. When an observer moves, then he finds the time slows down. So, meaning what has actually happened is, if this observer waited actually for 5 minutes, so he started his observation over here at t is equal to 0. If you are talking from this perspective, these charges were originally here. If he waits, this observer waits for 5 minutes. This observer waits for exactly 5 minutes. T is equal to 5 minutes. Then he will only find the charges reaching here and here, not here. So what he thought the path should be like this is not the real path. What he will actually get is this particular path. I'll just probably put it in this line, this color. He will get the path as this. He will get the path of the charges as something like this. It's slightly different than what was expected before. What has actually happened is, when this spaceship moves, for this person, 5 minutes has passed by. But when he thinks about this moving spaceship, because it is in motion, for that spaceship, 5 minutes has not passed. Actually, slightly lesser time has passed. Meaning, if on his watch, he sees, oh, 5 minutes are over, he will find in this spaceship, he will perceive the spaceship to have progressed in time, which is lesser than 5 minutes. Maybe, chumma for example, I am saying, this is not so much difference, but I'm just saying it is 4 minutes just for example. This is what is perceived. So think about it. If for this observer, this moving spaceship has only had a time progressing by 4 minutes, so obviously in those 4 minutes, those charges can't move so much. What was expected as seen by this observer? Yes. So understand that this observer feels that 5 minutes are over for him, but he feels that this observer has only his watch, or if he looks at the clock in this particular frame of reference of the spaceship, he will feel the clock in the spaceship has moved only 4 minutes. So obviously in 4 minutes, he will think that, oh, it has just moved only so much. It can't move or repel and cover the distance as expected. Getting my point? Did you love it? Yeah? Everybody, did you understand what has just happened over here? Isn't it crazy? So now you should understand that this observer, if he applied the laws of electrostatics only without thinking about relativity, he would expect these charges to be here, but they came out to be here. He would expect the charges to be at that blue solid lines, but it would be here. So he will feel that electrostatics is not answering my question. He will feel electrostatics is not answering my question. This position, you will get it using electrostatics concept, electric field concept. This is what you would expect, but the reality is over here. This is the place where actually it is. This is the actual position. This is the actual position. So definitely electrostatics is not able to answer it. So there will be something which is there apart from electrostatics or electric field which is causing that difference. So that difference has now come by magnetic field. We attribute it as magnetic field, but actually there is nothing like magnetic field. It is just that the time slowed down, and that is why the lens have contracted and all of that. So guys, because of that, the observer outside feels the charges would be here, whereas expectation will be here. So the difference of it, he will attribute the change, the difference, what he is expecting versus what is happening. Why is the change happening? So that difference, he will say, is coming because of this mysterious quantity called as magnetic field, because it couldn't be explained by electrostatic field. Got it? So magnetic field is just something what you see when charges are moving. But the issue is, sir, isn't this crazy to look at magnetic field this way? Absolutely right. Absolutely right. You are correct in thinking that whenever I have stationary charges, I get electric field. But the moment these charges start to move, they are in a different time frame of reference. So moving charge will not only produce the electric field, but also have a magnetic field perceived around it. But if you are with the charge, moving with the charge, if you are moving with the charge, you are in a static scenario, you are at rest with respect to the charge. So you will not see any magnetic field. But you just move out of the frame and let the charge go. Or forget, let the charge stay. Let you move. Let the charge stay. I am saying, even if you move, you will feel that there is magnetic field created by the charge. So even the charge literally need not have to move. Just you moving creates the magnetic field, or so called that perceived notion of magnetic field. But like I said, this is very crazy concept. So we cannot always think about relativity and solve the problems, because it will unnecessarily involve so many steps in between that we'll have to go through that entire process of thinking about relativity every single question. And we are not so geniuses like Einstein is, or maybe other people. So other people have great minds, but we say never mind. And that is why, to simplify all the process, we created this concept of magnetic field created by moving charges, alright, in a very simple way. And that is given by Biot-Savart's law. Alright. So now let's start with the concept. Satish, now you understood it? Okay. So we are just going to talk about magnetic field, but reality you should know, magnetic field is just electric field in a moving frame. That difference which is being created, that is what magnetic field is. But every time we cannot keep thinking about it. It's going to be crazy. So we're going to simplify it. And that is what the whole chapter is all about. Yeah. Sir, electric field and magnetic field are not exactly the same. Magnetic field comes because of electric fields in different frame. So it's not that only one of them exists. No, both of them can exist. Like for example, over here, this charge is moving, electric field is also there and magnetic field is also there. Both are there. Okay, both are there. The moment it stops, only electric field is there, magnetic field has vanished. But when it moves, it's both E and B fields are there. Alright. I hope Rasikuju, it is very clear. Alright. How time contracted to 4 minutes, that's a complete different concept. So I did not want to talk about how that time dilation happens. Maybe Einstein's relativity is a separate chapter in itself. It cannot be explained in 2 minutes, but you can check out different YouTube videos and you will understand it maybe slowly. So we'll not get there. We'll just assume that okay, it happens. And how do we explain magnetic field with that moving frame? That was our whole concept of this initial slides, okay, to explain what is magnetic field. Okay, now the concept of magnetic field generating from moving charges came from the famous experiment of Oersted, and Oersted took a current carrying wire, alright, it's basically a battery, and you take a wire and he sprinkled some iron filings around it, and these iron filings basically started arranging themselves in beautiful concentric circles. Iron filings are basically small particles of iron, and iron is known to be magnetic in nature, and in such a way that when magnetic field passes through these magnetic materials, they begin to align themselves like teeny mini compasses. Like the compass needle that you have, it aligns in the earth's north-south direction. Same way, these iron filings are like teeny mini compasses, magnetic compass which is used for navigation, and that is the reason why when current was passed and if you tap on these iron filings, let them loose and let them set in the direction of the magnetic field, they form beautiful concentric circles, showing that the magnetic field, because of this current carrying wire, is in the form of concentric circles, which is also true as a property of magnetic field. We have seen this. Magnetic fields can never start or can never end. They always have to be closed loops. There is no start, there is no end. We have discussed this. So it proves that, okay, experimentally also we can see the same thing. It's not like it starts, the branching happens and they merge somewhere. No, that is not what happens. And the direction of this magnetic field came out to be just like the right hand rule, thumb rule. So if you take a wire which is carrying, what is this? Sorry guys, this printing is wrong. Sorry, this direction is wrong. If the direction of the current, as the direction of the thumb, then the curled fingers, if this is the pen which is carrying current or the wire which is carrying current, if I place my thumb in the direction of the current, the curled fingers represent how the magnetic field lines will be curling. So if the curled fingers are like this, that means the magnetic field lines are going like that. If the curled fingers are like this, that means the magnetic field lines are going this way. So the right hand thumb rule in a way gives me the direction of the magnetic field lines in a around a straight wire carrying current. Alright, that is what this is. So let me just even change it. I think this diagram has come out to be wrong. I will just make this diagram later on. Okay, perfect. Cool. Now let us talk about Biot-Savart's law. Okay, because Oersted's experiment just proved that okay, moving charges is basically current and current creates magnetic field around it. Now every time our wires might not be straight, there could be bend or some curve in it. Alright, so it could be of any shape, it could have many wires also, and each of these wires might create a magnetic field. So what Biot-Savart's did was they made an expression to figure out how much will every small element of the wire contribute towards the net magnetic field. So if there are a bunch of wires and I am standing here, alright, I am standing here, I know all these wires will generate a magnetic field around it To figure that out, Biot-Savarts say, don't worry, you take a small part of the wire and figure out how much is its contribution. Like when you have to have a party, everybody contributes 5 rupees, 10 rupees. I don't know how much you guys contribute these days. During our times, we used to contribute 5-10 rupees. Maybe you guys contribute 5-10 lakh rupees for a party, or 5-10 thousand, or 5-10 100. I don't know. Okay. So everybody will contribute. This part of the wire will contribute. This part of the wire will contribute. Some other wire here will contribute. Some other wire there will contribute. Noting down everybody's contribution, but keeping in mind their contributions are vector in nature, because magnetic field is a vector. That means you need to worry about their directions too. So some contribution might be here, some contribution might be there, some contribution might be here. So, you know, all these teeny weeny contributions, if you add them up, you will get the total contribution due to all the currents around it at a particular location. Getting my point? So let's first figure out that how much is this contribution at a particular point. Later on, by integration or summation or addition of vectors, we can easily figure out how much is the total contribution at a particular place, okay, for the magnetic field. So let's define what are these numbers. There is a wire which is carrying some current I. So basically I is the current which is flowing in the conductor. dl is the small part of the wire where or whose contribution you are trying to find. So dl is the small part of that wire, infinitesimal current element we can call it, small element, and the length is always taken in the direction of the current. If the current flips, then the vector dl will also flip. dl is also the length of that wire. For that moment, it will be a small line segment because it is dl. Okay. What is r? R is where are you standing with respect to that current element. I am standing here, I am standing here, I am standing there. So it's a position vector. So r is the position vector of wherever you are trying to find the magnetic field. The contribution will not be large, it will be small. So it will be having dB. D stands for that small contribution. So magnetic field contribution at that point P. Theta is obviously the angle between that current element and that particular position vector. So these are the things which you should know for the formula of Biot-Savarts law. So what does the Biot-Savarts law come out to be? So the Biot-Savarts law comes out to be something like this. The magnetic field dB bar, comes out to be, there is a constant over here, which comes, and that constant is mu naught by 4 pi. We'll see what that constant is in a bit, don't worry about now, into I dl cross r, cross product with r, the whole thing divided by r cube, That's the formula for your Biot-Savarts law. Now you will see some places it is written in unit vector form also, don't worry about it. So we'll talk about first the generic form and then we'll see the unit vector form also. First, what are these terms? See, mu naught by 4 pi is a constant, let's ignore that. I is current, dl is that element, cross producting with r, okay, I have to take a vector product, and there is r cube, the distance or the magnitude of the position from the element to that point. I have to take the mod value of it. This particular constant over here, which is mu naught by 4 pi, has a value of 10 to the power minus 7. That is basically mu naught has a value of 4 pi into 10 to the power minus 7. Now this mu naught, just like epsilon naught, which was permittivity of vacuum, this is called as the permeability of free space or vacuum. Permeability of free space or vacuum, when there is nothing around, literally nothing, then this is the value. Just like in electrostatics, if you have a dielectric medium, the permittivity changes, right? Same way, if you have some magnetic materials, diamagnetic, paramagnetic, ferromagnetic, which you will learn later, then the permeability will no longer be this much. So the answer for your field will also change accordingly. For now, let's take vacuum or air, which have the same permeability almost. So, we'll not worry about different mediums for now. But you should know that at the back of your mind that this number is basically dependent on the medium which is surrounding that particular current carrying wire. That's all. Okay. So what does permeability tell me? It tells me how permeable those magnetic field lines are. Permeable means how can they, penetrate into something. Like we say some rocks are permeable, meaning easily the water can seep inside those rocks and maybe it can create some cracks. These rocks are impermeable, meaning those water from that lake or that river cannot go inside those rocks and they act like a nice barrier, like a waterproofing thing. Okay, so that is what the meaning of permeability is. So we are talking about permeability with respect to the field lines over here, meaning how permeable, how easily can those magnetic field lines pass in this region, which obviously depends on the medium. So let's always take vacuum. Now because there is cross product, if you want to figure out what the magnitude is, it's clear that dB will be nothing but mu naught by 4 pi, You will have I, you will also have dl. Cross product will be replaced by sine of theta, which is the angle between L and R, and this R and this R cube will obviously cancel and I will be just left with R square. So this then becomes only the magnitude. Notice how R cube has become R square. For those of you who did not get it, if R was there, this would be cube. So if I cancel out one R, it will become square. Is that making sense? So that is why this is the magnitude of the field due to that particular element. But that's okay. We will always remember this one. Now what some books do is they take this particular formula, which is dB is equal to, yes, you write mu naught by 4 pi, as it is. IDL also as it is, guys, no change in that. IDL bar as it is. But over here below, instead of putting R cube, what I do, I put R square deliberately and I will do cross product with R bar, and because technically R cube should be there, I will put that remaining R over here deliberately. Okay, I just manipulated this equation, nothing else. What is this number over here? Think about it carefully and answer. What is this number over here? Come on. This is obviously IDL. Okay. What is this number? Yes, it is a unit vector along that position vector. So it is cross producted with R cap. It is that unit vector and then you will get R bar. So R cap is unit position vector. But this is just a vector form. There is nothing great about it. I mean, we will not try and remember it. Okay, it's fine. I mean, if you know vectors, this is very laddu thing. So there is nothing great about it. For us, this formula matters, and that's all that I care about. Okay, cool, everyone? Perfecto. So what's the unit of permeability? You can figure it out from here only. It's not that difficult. Say for example, if you see on the left hand side, we have Tesla, right? We have Tesla. Here we want to know what is the unit of mu naught. Then we have current, basically. We have current which is measured in amperes, ampere. And then you have length, IDL cross. So you have meters also. And if you just look at this expression, IDL sine theta is not having any unit. R square is there. That means meter square is there below. obviously what we can do, we can cancel off 1 meter and 1 meter over here, and then we can move it around so that we get what would be the SI unit of mu naught. What will it be? It will be Tesla meter per ampere. Tesla meter per ampere. Is that clear, everyone? Yep, perfecto. Amazing. Good evening, Shilpa. Hi, Samir. Good evening. All right. Music, though, maybe we will be taking more question solving sessions later on. That time you will understand it. And meanwhile, I would say solve HC Verma, the solved examples, concepts based, conceptual questions, objective questions 1, then 2, and the basic exercise questions. Then go to any other book, whether it is DC Pandey or Cengage. That's okay. Right? Do that. Sheikh, which part? Let me know quickly. Then I can help you with that. So, just to quickly recap, we just saw that Oersted said that whenever you have a current carrying wire, it produces magnetic field around it. But then how much is that magnetic field and what is the direction is given by your Biot-Savart's law. So, they said that whenever you have multiple wires, each wire might contribute in different way. So, you take a small part of the wire and try to figure out the contribution of that small part. And the contribution of that small part, dB, is a constant, just like permittivity was 1 epsilon naught and Coulomb's constant was 1 by 4 pi epsilon naught. Here it is mu naught by 4 pi. And that mu naught has a value of 4 pi into 10 to the power negative 7. Great. Into I into dl cross r. So, here if you do dl cross r, you will see the thumb is going inside. That means at this point, the magnetic field should be going inside. Because dl is there, r is there. Right hand thumb rule. A cross b, dl cross r. So, the thumb goes inside. Divided by r cube. If you look at the magnitude, this r will get cancelled and only r square will be remaining. If you write it in unit vector form, what I have just done is this r cube, I have written it as r square into r. But we all know r bar by r is a unit vector. So, I can replace it with a unit vector symbol also. There is nothing wrong about it. Okay, cool, perfecto. And then we also figured out what is the unit of mu naught. This was Tesla. Which formula have I used? This formula. dB is mu naught by 4 pi I dl sine theta by r square. dB is measured in Tesla, magnetic field. Mu naught, I don't know. Current is in ampere. dl is in meters, ampere and meters. And bottom, we have basically meter square. So, that is why I got Tesla meter per ampere. So, that was the unit. That was the unit of mu naught. Great. Now, before going ahead, let me also remind you, if you have multiple wires, then what do you do? Or a wire which is in general long or whatever you can say. So, say for example, you have a long wire or long wires carrying some currents. Then you will take a small element like this, dl, and then you will take a distance like this, which is r, and at this particular point we will figure out what is the magnetic field due to this small element. dl cross r will go inside. So, I just put dB vector over here. So, the total contribution, so I will say the net field, the net magnetic field, B vector will be integration of dB vector. So, it will be nothing but integration of dB. Each dB will be nothing but mu naught divided by 4 pi. You will also have I into dl and cross product it with r vector, whole thing divided by r cube. So, when you integrate it, whatever answer you get, my dear, that is the magnetic field. That is the magnetic field. More than that, I would say this is what it is that we have done. Correct? You're just integrating all the small magnetic fields. Yes, I'll be doing questions also. Definitely. Right. Yes. So, let's do a question based on this, which was asked, I think, in 2024 or 2023. This is a previous year question. There is a small element whose length is delta x I cap it is placed at the origin and carries a current of 10 amperes. The field on the y-axis at 0.5 meters of the element delta x, whose length is 1 centimeter, is how much? So imagine there is a long wire. Out of that you have taken a small element. Due to this element at this point, what could be the magnetic field? As you can see, that particular element is right now facing in this direction. This is the direction of dl vector. Also notice the position of the point where you want to find the field with respect to the element is over here. So this is my r vector. You can think of it like that. This is my r vector. So if I do dl cross r, use your right hand, place the 4 fingers here first and slowly curve it like this. The thumb will come towards you. So if the thumb is coming towards you, that means the magnetic field at that particular point is also towards you. So that dB is over here. But the question is, I think, only the magnitude, not the direction. But if direction was asked, then it will be in the k cap direction, or dB bar is along basically z axis. This is not asked, but if it was asked. Okay, now let's figure out how much is the magnitude of it. I'm not interested in the direction because the question only predicts the magnitude. So what will I put first? Mu naught by 4 pi, whose value is nothing but just 10 to the power minus 7. Then you should put current into dl. Here the current is basically 10 amperes. The length of that segment is 1 centimeter, meaning 10 to the power minus 2 meters. Then you should put sine theta divided by r square. I'm only interested in the magnitude. Remember here the angle between r and dl is 90 degrees. So it will just be sine of 90 degrees, whole thing divided by the distance. Distance is nothing but 0.5 and that will be squared. That's all, guys. That's all that is there. So this 10 and 10 raised to minus 2 will cancel. 1 minus 1 will be there. So this will become 10 raised to minus 8. Sine 90 will be 1. 0.5 will become 0.25, guys. 0.25 is 1 by 4. So 4 will come on the top and 10 raised to minus 8. Answer is always in Tesla. So 4 into 10 to the power negative 8 Tesla is the right answer. Got it? Everyone? How many of you got the first answer? Yes, the answer is option 1, correct. Is H.C. Verma enough? No. Is H.C. Verma good? Enough? No. Is H.C. Verma good? Yes. What you should do more than that? Basically solve PYQs and your coaching modules. If they are good, if they are not good, then you will have to go to other book modules like Physics Galaxy or SL Aurora or other things, guys. Basically DC Pandey, Cengage, all these books. So it also depends on your coaching modules. Some coaching modules are really good. So I won't take names, but you know it already. So some coaching modules are really good, guys. So it's not about this institute or that institute. Many coaching modules are good. So just use them, okay? And don't just run behind many books here and there. So if your coaching is giving, just use it. That's all. Simple. Otherwise, use H.C. Verma, DC Pandey, Cengage, Irodo, standard books. Correct? Okay. Now, let us try to figure out the magnetic field due to a wire which is bent in the form of a loop, meaning a circular coil carrying current. So look at this, the current is going here and it is going around and coming back. So it's a coil of current, and if I know that every element is going to produce a magnetic field, 100% all these elements will contribute together and they will generate a magnetic field around it. Now the best part about magnetism is always there is some kind of right hand rule which works. Now let me warn you, if you are not a JEE student, or rather even if you are a JEE student but you are very I would say sincere and you have your loyalties towards CBSE or NCERT or state board, then you might not be so fond of right hand rule. Rather you will be using some stupid rules like this left hand rule, right hand rule, this is FIB, this is ILV, this is QVB, this is that. My goodness, guys, swimmer rule, right hand cock rule, right hand that rule, swimmer going that side rule, nail hitting the screwdriver and the screw rotating that rule, left foot in your mouth rule, left foot taken around your neck and hitting on your head rule, all these rules, just throw it up aside. You just need one rule, and that is right hand rule, nothing else you need. That's all. Most of the times, not most, in fact every time, there is not most, wrong word guys, every single time your right hand rule is more than enough. Here also you will see that if you take the fingers of your right hand, curl it in the direction of the current, automatically the thumb tells you the direction of the magnetic field. The fingers curl like this, thumb points up, the magnetic field is going from inside to outside like this. I think some arrow marks are again wrong over here. Yeah. That's all. If the current flips in direction, if it goes like this, then you will see the magnetic field lines will come inside. That's all. Okay. So that is what this is. Just 1 second. Now it all makes sense. I don't want to give you wrong directions over here. It should go all like this, right? Outside, outside. So some of the directions just got flipped in this. Now it's fine. Okay. So curling your fingers. So I'll just mention that over here. Curling your fingers in the direction of the current. So these are your 4 fingers. So fingers, curl fingers along the current, automatically your thumb which is there, then your thumb is along magnetic field. Very, very simple. Okay, nothing great to remember. Curl your fingers, thumb points in the direction of the magnetic field. Curl your fingers opposite, it goes exactly down. So now let's figure out how much is this magnetic field. So for that, let me take a current carrying coil and let us just say the current is I. Let us just say the radius of this particular loop is, let's say, R. Okay, and then I want to figure out what is the magnetic field at the center of this particular coil. I want to figure out what is the magnetic field at the center of this particular coil. Okay, so let's find that out. First come first, what I will do, I will just take a small element, maybe like this, and I will call that as DL. Okay, that is a DL bar. That DL bar will try to figure out how much is the magnetic field over here. So I will call this as my position vector. It is making 90 degrees. DL is always in the direction of the current. So if you do DL cross R, you will see the thumb coming towards you. So the magnetic field contribution due to this dB will be towards you. I am more interested in the magnitudes, so let's focus only on the magnitudes, guys. So my dB will be mu naught divided by 4 pi, current into DL, current and DL as it is, nothing changes over there, into sine of theta, here it will be sine of 90 degrees, whole thing divided by the distance square, so basically R square. But guess what small r is? It is always R. Always R, no matter where you take the element. Even if you take the element here, it is R. Even if you take the element here, it is R. Even if you take the element here, it is still R. So small r is always the radius of the loop, which is a good thing because now everything in this is a constant except for DL. So I can very easily say dB is equal to, my mu naught is there, 4 pi is there, I is also there, DL is also there, and then you also have R square. Great. So therefore, the net field at the center center of the coil will be integration of dB, and all these dBs will be towards you, no matter where you take. Even if you take an element here, dl is there, r is here, so dl cross r is towards you, dl cross r towards you. So every single current element is helping and adding up to the contributions. So the total magnetic field will be a simple addition, dB, 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 that's all. So integration of dB, there is no need of any kind of components. So that is why this will come out to be just, if you substitute all of them, which is mu naught is there, you also have 4 pi, you also have I, you also have R square, you also have DL. So lot of these people are going to just come outside. You will have mu naught by 4 pi, I divided by R square, integration of DL. But we are integrating this across a loop, and when you add all these DLs, you will get the circumference. So this will be mu naught, then you will have 4 pi, then you will have I, then you will also have R square, and integration is circumference, so it will be 2 pi R. Oh great, so 2 pi and 4 pi cancels, you will get 2, R and R also will cancel. So guys, you are just going to get mu naught I by 2 R, that's all. Mu naught I by 2 R, simple. That is the formula, guys. So whenever you have a current carrying loop and you want to figure out what is the magnetic field at the center, the magnetic field is simply mu naught into current divided by 2R. That's all. Mu naught into current divided by 2R. Is that clear? But let's say there are n windings on that current loop. Okay, so let's just say there are n number of windings on that particular current loop. Just showing like this. Just 1 second. Yes. So if there are n number of windings, n number of windings, then each of them will contribute the same amount. So the total magnetic field at the center will be all of this just multiplied by n. That's all. So that becomes your formula. So the magnetic field at the center due to n number of windings of that particular coil will be mu naught I divided by 2R, whole thing multiplied by n. So components on the opposite direction with equal magnitude, no, they will not cancel out even on the opposite directions. I'll tell you why. Just think about it. See, if this is that thing, if you take an element here like this, R is over here, DL cross R will be towards you, okay, like this. You take an element over here, the arrow mark will be like this, R vector is like this. So if you do DL cross R, it is still going to be towards you. So no matter where you take, alright, it is always going to be towards you. You can see, even if you go on the opposite side, I know what you felt. Sir, I have flipped the direction of length. Correct, but you have also flipped the direction of R vector. So two things are flipping. That is why it is just ending up to be the same direction. Is that clear? Okay, great. So that is the answer to your question. Now, sometimes what happens, you might not get multiple coils, rather you might just get an arc of it. That is also a very, very common question. That is also a very, very common question. Say you have just this much part of the circular loop. Circular loop is huge, but you are taking a small arc of it. This is current I, and this is the center, this is the radius, this is the angle. Now exactly at the center, again if you use your right hand rule, guys, the fingers will curl in the direction of the current. Current is going like this, the thumb will go inside. So the magnetic field in this situation at the center will be exactly inside. Sir, what will be the magnitude of it? I will ask you a simple question. If it was a complete circle, then the magnetic field would have been mu naught I by 2r. But if it is half of that circle, then it will be mu naught I by 2r into half of the total circle. Correct? If it was quarter of a circle, then it will be 1/4 of the field as generated by a complete circle. Meaning, how much magnetic field is generated at the center, it depends on how much part of the circle are you considering. Because if there are n windings, so you are multiplying it by n. One circle is mu naught I by 2r, 2 circles is into 2, 3 circles is into 3, and so on and so forth. So if it was half a circle or quarter of a circle, this n will change to half, 1/4, 1/5, 1/6, 2/5, whatever that fraction is. So instead of thinking of what n could be, we could immediately write it in terms of the angle. So here the number of turns will no longer be complete, rather it will be the fraction of the circle, the fraction of a loop, and that fraction, my dear, will always be theta divided by 2 pi. Correct? If it is 180 degrees, so 180 by 360, which is half. If it is 90 degrees, 90 degrees divided by 360, which is 1/4. So if I put theta in radians, so automatically you will get the answer, if you use this formula as the fraction of that loop. So that is the reason why we can easily write down the magnetic field magnitude. The magnetic field magnitude will be mu naught I by 2r, but here you put theta by 2 pi, but we all know this 2 pi into 2 will become 4 pi, so we can rewrite it as mu naught by 4 pi into current divided by r multiplied by theta. Should I remember this or this? I suggest don't remember anything, because it should come naturally to you that, sir, if it is 1/5 of a circle, naturally it will be 1/5 of the magnetic field. So no need to by heart as such, but you should understand the concept behind it. That's all I would say. Okay. Otherwise, this formula is not very different from this. Okay, but it can be confusing. Sir, here 2r was there. Sir, here 4 pi r is there. Sir, pi was there or not there. So if you go like that, obviously, man, the formulas are going to be difficult for you to remember. But don't look at the formulas like that. Think like this. Okay, for a single loop, I know, right? Mu naught I by 2r. So for 3 loops, 3 windings into 3. So for 10 windings into 10. Half of the loop into half. 1/4 into 1/4. That's it. So if you look at it like that, mu naught I by 2r into how many windings or how many turns? Whether it is more than 1, less than 1, doesn't matter. Clear? Everyone? Understood this particular concept? Very good, very good, very good. Amazing. Now, before going ahead, let me also tell you, although the heading is wrong now for the next point. If you have a wire which carries current, see, if you are on the top, then see guys, this current is going like that. So hold your thumb in the direction of the current. The fingers are going to give you the direction of the magnetic field. So the magnetic field will go from behind this wire and come towards you from the top, and it will go below and it will go inside the plane of the board. So meaning the magnetic field will come towards you over here and it will go inside the board below over here. But what will happen if I stand anywhere on this line or even over here or over here? Then the answer, my dear, is always going to be a big fat 0. It will be a big fat 0. Okay. So on the line, no matter how far close you are, the magnetic field contribution is 0. One simple way to look at it is, see, if you do I dl cross product it with r, notice how r vector and the length vector are going to be in the same direction, which means sine of 0 will be 0. So I dl cross r will be also 0. That is why magnetic field is always 0 on that line or on that axis. Okay, no matter how long or small that wire is. Yeah, perfect, amazing, amazing. Sir, if two contents are present, we can use right hand rule. Use then contents present like FBL. How can we solve it, sir? If two contents, I didn't understand what do you mean by two contents, Satish. Two contents means two currents, you mean. Even if you have two currents, three currents, doesn't matter. Okay. Yeah. And Zainim, sir, I have given the exam 2 years of my life. Man, first of all, let me tell you that you studying for the exam has no obligation on the exam that the exam has to clear you. Okay. So first of all, come out of that mindset. Doing efforts, not just for exam, in life, no matter where you put in the hard work, does not mean you have to get the results. It is your duty. You have made that choice, so you are doing it. So understand, don't try to think whether I will get results, whether I will get IIT, because if you start expecting like that, then 100% you will be demotivated. Rather, I would suggest, I will do my best. Let's see what happens. Don't even think whether I will get All India rank 10 or All India rank 1 lakh. It doesn't matter. You are putting in your effort. It will come in some way or the other. And even if you do not get a rank, doesn't matter. You will do something else in life. You will do something good in life eventually. Okay. So there is no point thinking about the result of the exam which you have not yet given, and when there is still, sufficient amount of time left. Is that right? All right. Okay. Let's do some questions coming up on your screen, and here is the first one. Okay. Let's do this one first. Two concentric current loops of radius r and 2r carry currents I and 2I respectively in opposite directions. The magnetic field at the center is how much? Okay, let's try to think. So first loop and second loop, okay, r and 2r. So this is basically r, this is basically 2r. R is carrying current I, okay, let's say current I like this, and 2I respectively, but in opposite direction. That means this is basically 2I. So if you look at it, current I, which is the smaller loop, if you curl the fingers in the current, the thumb comes towards you. So the smaller loop is generating a magnetic field towards you. So I will call it B1. And how much will that B1 be equal to? Mu naught current divided by 2 into R. Now let's look at the bigger loop. The current is going opposite way. Curl your fingers in the direction of the current. Thumb automatically is going inside. So the second magnetic field due to the bigger loop carrying current is inside. How much will this B2 be? It will be mu naught. Current is 2I divided by 2 multiplied by 2R. 2 cancels. Mu naught I by 2R remains. Guess what? They were both of the same magnitude. So if I try to find the net magnetic field, answer will be obviously 0. Because keep in mind, this was inside and this was outside. So they are two different directions, exactly opposite, but same in magnitude. So they will end up cancelling. Hence the answer to this question will be a big fat 0. Getting it? Option 1? Yes, very good. Excellent. Moving on to the next question on your screen. A wire of certain length is bent into a single loop turn carrying current I. The magnetic field is B. Now you bend it into 2 turns. So how much will the magnetic field be? Initially it looks like a simple laddu question only, but I don't think it is such a laddu question. If this radius is R, some current is I, the magnetic field, let's take like this, say current, the magnetic field is then going to be towards you. It will be mu naught into current divided by 2R. But now what you are doing is you are bending it back into 2 turns. Okay, So what has happened is now there are two turns into that loop. So when there are two turns, current is still the same. Question is, what is the new magnetic field? My question to you is, if you thought, sir, there are two turns, so magnetic field will double, you are thinking very narrowly, you are missing a bigger picture. Yes, it will multiply by 2, but do not forget, even the radius will change, no? It's the same wire. Yes, your total perimeter length should be constant. So initially the length was, if I say 2 pi r, and there was only one round. Later on, whatever that radius is, it will be 2 pi small r but into 2. There were two rounds. So small r is capital R divided by 2. Small r is capital R. This 2 comes below this r, so r by 2. So here, when I try to find the new field, yes, it will be mu naught into current divided by 2 small r into 2, but this radius has changed. Do not forget that. And that, my dear, is r by 2, okay, and into 2. So that 2 goes on the top, so it will be mu naught I by 2r and into 2 into 2. What is this number? This is nothing but the old magnetic field. 2 2s are 4. So the magnetic field has become 4 times, which is C for Captain Shreyas. Is that right? Option C. Yep, it is going to be 4B, guys. Yeah. But if force, magnetic field and current, force, magnetic, even for that, Satish, QV cross B, and whenever cross product is there, you always can use right hand rule. So why do you need some left hand, right hand, Fleming, that, blah, blah rule? Nothing. Q, V is here, B is there, okay, V cross B, force, that's it. Velocity is there, magnetic field is here, okay, V cross B, force is here. That's it. Always use right hand rule, man. You don't need anything else. Okay? Great. Moving on now to the next question, but before that, again, see, if you remember the first diagram which I had shown, how the magnetic field is. Right now what we are focused is only this point, but there is magnetic field literally everywhere. So remember, in JEE syllabus, we don't try to figure out what is the magnetic field here or some random place anywhere. We just focus on magnetic field at the center, because finding the magnetic field at some awkward random position is quite difficult and the formulas are not so easy to figure out. So that's why we focus at the center and anywhere on this line, basically. In fact, that line is called as the axis. Notice how the fields are concentrated, dense over here. So the field is strong here. But as you go away on this line, which is also called as the axis of that coil, the fields diverge. So as you go far, the magnetic field strength reduces. And we will also see what is that answer. So what could be the magnetic field on the axis of a coil? Magnetic field on the axis of a coil. So this is the axis, and on the axis I am standing at some distance x. The coil has a radius of r and it could have some current, maybe let's say like this. This is the current. The magnetic field at that particular location, let's say, is like this. Now, when you try to find the magnetic field in this scenario, then the derivation is slightly lengthier. I'll just give you an idea of it. Will not sit and do it over here, but you should have an idea. That's all. So I'll tell you what really happens. You take small elements of currents just like before. Okay. So let's say we take a small element over here. This particular small element is coming towards you. Try to visualize it. It is coming towards you. So this particular small element is coming towards you. And for this element at this particular point, if you draw the position vector, this will be the position vector. DL is coming towards you. Visualize it in 3D. I cannot draw 3D on a 2D surface. The R position where you want to find the field is here. So if you do DL cross R, the magnetic field comes that way. Look at my thumb. DL is towards you, cross R, the magnetic field, the thumb direction is this way. So the small teeny mini magnetic field will come like this, guys. This is very, very interesting. So the magnetic field will come basically like this. Now this magnetic field will have two components. One component will be here, okay, and the other component will be basically like this. Other component will be like this. Okay, now let's understand. So if you notice over here, if this particular angle is theta, this is 90 minus theta, this is also going to be theta. So that component which is here will be dB sine theta, and that component which is here will be dB cos theta. Okay, perfect, everybody. Now you take any such element, rather I would suggest take the exact opposite element. So if you happen to choose the exact opposite side element, here the current was coming towards you, here the current is going inside the board. This was also R, this was also position vector. How will the magnetic field lines look like? Well, for this current coming towards you, the magnetic field was here. For this current, the magnetic field will be here. Okay, you can visualize it. It's just like taking this DL and R vector, just taking it like this and coming over here. Okay, just visualize. DL was here, position vector was here. Just go around the loop and come over here back. That's it. You just done that. Current is going inside, position vector is here. So even the magnetic field which was here, that will also turn and it will go like that. That is all. So you will see there are these dB sine theta components which end up assisting, helping, adding, but dB cos theta components which are ending up cancelling out each other for every such two opposite, diametrically opposite elements. So these end up cancelling out. They are cancelling. But these two end up adding. Now if you do that for every pair of opposite elements in that circle, these two, all of them, the dB cos thetas will cancel, dB sin thetas will add up. So when I try to figure out what is the net magnetic field on the axis of the coil, understand it will be just the integration of dB sin theta. dB sin theta. Getting my point? Only dB sin thetas will add, everything else which is these components will end up cancelling. Solving that only we will get the answer. Solving that only we will get the final answer. I am not doing the complete derivation, but you should have an idea of how it is coming. That's more than enough. So this particular magnetic field comes out to be, notice magnitude wise, you will have mu naught definitely. You will also have current from here, and then you will have divided by r square plus x square, whole thing raised to 3 by 2. You also will have the number 2 over here, mu naught I by 2, okay, and then lastly over here you will have r square. That's it. This is the answer. Now as a special case, do one small favor for me. Substitute x is equal to 0. If x equals to 0, that means you are at the center of the coil. If x is 0, what will the magnetic field will be? Mu naught by 2, current, r square divided by r square plus 0 raised to 3 by 2. This will be nothing but mu naught by 2 I r square. r square raised to 3 by 2 is nothing but r cube. So solving this will be nothing but mu naught I, r square cancels, 1 of the r remains. Exactly what we would expect at the center of the coil. You have derived this, right? Mu naught I by 2r. Forget that n, but that's what it is. So that's exactly what you will get. That means this is a more generic expression. In a special case, if you are at the center, then you still get the magnetic field. So this formula obviously you should remember, guys. Everybody clear? Okay, how to figure out the magnetic field on the axis of the coil. All right. Amazing, amazing, super. Studio tour, yes, maybe someday, man. Maybe not today, but trust me, if you see my studio, right, you will feel like, sir, are you serious? Everything looks so neat, clean, but my studio, it's like a Batman's cave when there is no light. There are like mosquitoes breeding, they are having families. Yes, a lot of families are staying here of mosquitoes because it is so dark when I turn off the light, and most of the day when I'm not teaching, then it is dark. So a lot of creatures are living over here. So I don't know, every day I find something. That day I found a lizard, some rodents, some mosquitoes. Yeah, so it's like that. So I literally have to think about all of these families living out here. Yeah. Anyways, so that was magnetic field on the axis of the coil. Let's move to the next question. A circular loop of radius r carries some current. The ratio of the field at the center of the loop to the field at the distance r root 3 on the axis of the loop is how much? Simple and sweet question it is, but let's understand. First, the magnetic field at the center, which we know. So let's just put it over here. Magnetic field at the center, we all know is mu naught I divided by 2r. But we are now interested in magnetic field on the axis. Let's rewrite the formula. Mu naught I r square divided by 2 r square plus x square raised to 3 by 2. Okay, great. So mu naught is mu naught, I is I, r is also r, 2 is also 2, r square is r square, x is what this distance is. Distance on the axis. Notice that is what your x was. How far from the center you are on the axis. So this was called the axis of the coil. This was the axis of the coil. So that distance is clearly mentioned as r root 3. So put r root 3 over here and square it, and then put the number 3 by 2. Let's see what do we get. Mu naught current r square, whole thing divided by 2, and then you have r square plus this square is nothing but 3r square whole raised to 3 by 2. So this will be mu naught current r square whole thing divided by 2, and then r square plus 3r square is 4r square. So we have 4r square raised to 3 by 2, meaning square root is taken and then cube is done. Alright, this square root I know it's a perfect square. So it will be mu naught I r square divided by 2. Square root of 4r square is nothing but 2r, and then the number raised to 3. Okay, so that will be mu naught current r square whole thing divided by 2 into 2 cube is nothing but 8, and then you have r cube. Okay, so that will make it mu naught current r square cancels, 2 8s are 16, and then we have just the number r. But that is not the question. The question is finding the ratio. So to find the ratio, we'll have to just take mu naught I by 2r whole thing divided by mu naught I by 16r. Mu naught, I, r cancels. So 1 by 2 by 1 by 16. So 16 by 2, which is the number 8:1. So 8:1, which is option C, bacha. Okay, so 8:1 is the right answer. So this calculation is purely algebraic. The physics part ended here only after you substituted. Once you know what is what, that's it. After this is pure simple algebra of 9-10 standard level, nothing great. Okay, so the answer is 8:1. This question has come so many times in JEE. You can see PYQs. Most of the times this question has come. Now this question also has come multiple times in JEE. So I am going to give it to you as homework. Here the question is exactly reversed. Instead of giving you the distance and finding the ratio, here the magnetic field is already given. It is B/8 or the ratio is given. You have to figure out how far is that point. So at what distance? It's exactly the reverse. So think about it, you will get it. Okay. So will you be able to solve it? Where will you post the answers? In the comment section after the video is over. We are nowhere close to the end of the class, but just telling you. Okay. So that way I will know if you are watching the class, you know, till the end or till the middle, because some people just skip, go somewhere else. So this is a way to check. Okay. So try this out. If you are smart enough, you would have answered it by now, but anyways, cool. So let's go to the next thing. Magnetic field due to a straight wire. We already saw this in Oersted's experiment that if you hold your thumb in the direction of the current, you automatically get the direction of the magnetic field, right? We already saw that. Okay. Now, how much is this magnetic field is the real question. So let's try to find this out. So for that, let's say again, you are standing at some location. Let's say you are here. At that particular location, let's say the magnetic field at that place is B. Okay. The distance from the wire, I will just call it as R. It is the perpendicular distance. The current is I only. We'll just keep it as I for now. Okay. This current is I. Okay. What I need apart from this is how long is this wire. But the formula does not include the length. Rather, it includes how much angle it subtends at this point. If the wire is long, the angle which it subtends will be more. If the wire is small, the angle will be small. Meaning something like this. You just have to draw a line from the point where you want the field to the end point of the wire, where the wire ends, and same thing on the other side. Okay. So take the point wherever you want to find the field and join it towards the end point. It could be anywhere. Sir, what if it is infinitely long? Then it will become like this. If it is small, it will become like this. So right now it is ending here. Just leave it there. We'll figure out about infinity in a bit. Don't worry. One of these angles I will call it as alpha. The other angle automatically will be beta. So this particular magnetic field B will come out to be, observe it carefully, it comes out to be mu naught by 4 pi, current is also there, in fact R is also there, mu naught I by 4 pi R, but these angles also come, and the angles come like this, sine of alpha plus sine of beta. That's it. That is the formula. Mu naught current by 4 pi R sine alpha plus sine beta. These angles decide how much of that length of the wire is there, which is carrying that current, contributing towards the field. R decides how far you are, because if you are far, the field strength will change. If you are close, the field strength will reduce. That's all. This is all that is there in the magnetic field due to a finite wire. So this is basically magnetic field due to a finite wire carrying current. That's all. How this is derived, that is another story. So what happens is, just giving you an idea, we will not do the entire thing. So you just have that wire, let's say like this, which is carrying that particular current. You take that distance, let's say it is over here. This is your R. This is your R. You take any small element, of wire carrying current. Let's say over here. This is that small element of wire which is carrying current. Now, what I will do next is I will draw the position vector. This is that position vector. So for position vector, actually we use this symbol R. Now we have already used that, so it's okay. We will use different R over here. Here R is position vector, capital R, and it will be like this, This will be that angle theta, and at this point, if you do dl cross R, it will go inside. So the magnetic field at this particular point will be inside like this. Now, this dB will obviously be mu naught current dl sine theta divided by 4 pi, and then you have capital R square. But you integrate this from this point to this point, that's how you get the net magnetic field. So integrate it with proper limits, because these angles, this theta will definitely keep changing. When you go on the top, it will be different, and when you go here, it will be different. So you put the limits accordingly when you are here versus here, and you integrate all the contributions, you will get basically this formula which I have written here. Okay, so I hope you understand. It is again coming via integration only using Biot-Savart's law, nothing different from it at the end of the day. Okay, cool, very good, amazing. Now let us take some special cases of that, because that is what makes this very interesting. So let's say we have a very long wire. So this is a long wire, long conductor. This is a very long conductor carrying some current. That means it is infinitely long. Long means very, very long. You are again standing over here at some distance like this. So what will be the end points looking like? Because it is going till infinity, when I try to find the angle subtended at this point, this infinity will come literally so far that this line will go far like this, and it will make such a big angle that it will be almost 90 degrees. Same logic, the other end will be so far away that when you try to look at the end, it will almost be like this. So my dear warriors, can you see my alpha is basically 90 degrees. The same story is with beta, that is also 90 degrees. So when I try to figure out what is the magnetic field, right now it will be inside. Okay, what will be the magnetic field? It will be mu naught by 4 pi current divided by R sine 90 plus sine 90. Sine 90 is 1. So it will be mu naught by 4 pi I by R, 1 plus 1, which is nothing but 2. So mu naught by 4 pi I by R multiplied by 2. 2 and 4 will cancel, and you will get mu naught I by 2 pi R. Crazy. This is due to a long wire. Now this formula, please remember it. Mu naught I by 2 pi R. Compare this now with circular coils magnetic field. Pi was not there, that's all. Look at it. This is for a long wire carrying current, infinitely long wire. Look at what the magnetic field was due to just a loop of coil. Mu naught I by 2R, there is no pi in this. So you should know when pi will come and when pi will not come. So it so happens that when you take a circle, and circle is usually associated with the number pi, because pi came from that circle, correct? Over there, pi value does not come in the formula. Circle we usually associate with pi. But in the magnetic field formula, pi is not there. But for a straight line, for a straight long wire which is carrying current, there pi is there. So it's opposite of what it is associated with. That's how you can Remember it as a trick. Okay. Yes, music, moving charges produce magnetic field, and there is nothing like absolute rest and absolute motion. So always a charge will be producing magnetic field in some or the other frame, and there will always be a frame in which it will be at rest. So you will always see it will be producing only electric field in certain frame. Yep, you can say that. Definitely music ethic. I hope I have answered your question. Yeah. Tushra, which opinion man I should tell? Okay, this was infinitely long. What about semi-infinite? What about semi-infinite? What is the meaning of semi-infinite? Semi-infinite means something like this. It goes like that. The endpoint on one side is very, very clear, but the other endpoint is not. This is called as a semi-infinite conductor. Semi-infinite. On one side it goes to infinity, other side we know the endpoint. So what happens in such cases? The one end is really far, so the angle alpha, that you see will definitely be 90 degrees. But the other side, it is not anywhere here, but it is here only. So it literally coincides on it. So therefore, the beta value will be 0 degree. Did you realize why beta is 0 and alpha is 90 degree? Because the other end is literally in front of you. So there is no angle with the perpendicular. So when you try to find the magnetic field, it will have mu naught current by 2 times of R, sine of 90 plus sine of 0. Sine 0 is 0. Sine of 90 is obviously 1. So it will be nothing but, oh sorry, this was 4 pi, my bad. 4 pi R, 4 pi R. So this will be mu naught current divided by 4 pi into R. No need to remember it, but you should know how to solve for every kind of scenario. Alpha and beta are given to you, immediately you can get the answer. Cool? Perfect? Wonderful. Let's do now some questions based on this. An infinitely long straight conductor carries a current of 100 amperes. At what distance from the conductor is the magnetic field caused by the current equal to 0.5 into 10 to the power minus 4 Tesla? It was a PYQ question. So let's solve. Because it is a very long wire, we know the magnetic field formula is mu naught I divided by 2. If I am confused about pi, I think for a circle pi is there associated, so pi in the formula is not there. For a straight line, pi is not associated, so pi is there in the formula. So it's exactly of what we feel. So 2 pi r. So magnetic field is 0.5 into 10 to the power minus 4. Mu naught value is 4 pi into 10 to the power negative 7. Current is 100 amperes, okay, divided by this number 2 pi and obviously r. Couple of things start getting cancelled. 2 pi and 4 pi, that will go 2 times. These two zeros with this will become minus 5. Is that right? And on this side, I can obviously write it as 5 into 10 to the power minus 5. I've shifted the decimal. Here I will have 2 multiplied by 10 to the power minus 5 and r. Oh, interesting. Minus 5, 10 to the power minus 5 cancels. So my r will be 2 is there as it is. Bring this number 5 over here. So it will be 2 by 5, but of a meter. If you want to convert this into a centimeter, because everything is in centimeters, multiply by 100. That's it. So that answer will be in centimeters. 100 by 5, that's 20. So 2 into 20, that's 40 centimeters. So 40 centimeters should be the right answer. Got it? So this kind of calculation based questions could be rare, but it can come. It has come. This is one of the PYQs. Shall we go ahead, guys? I hope you understood how to apply these formulas. That is very important. Once you know how to apply it, you can solve any complex questions. Next question on your screen. Two long parallel wires carry current I1 and I2 when they are in the same direction. The magnetic field at a point in the middle is 10 microtesla. If one of those currents is reversed, the field at that same point becomes 30 microtesla. What's the ratio of I1, I2? It's a crazy nice question. Let's solve it. Okay. It's a very good question, guys, because you need to get the directions right, and also it is procedural, and you need to solve it properly with proper calculations. So two wires carry current I1 and I2. When currents are in the same direction, let's take current here and let's take current here. So this is I1, let's say this is I2. So if you take this current and place the thumb like this, the fingers go like that, the finger is going inside the plane of the board, that means the magnetic field is inside due to the current 1. If you take current 2 and hold your thumb like this, the fingers will curl like that, they go behind the conductor and come towards you in the front from the left side. So the magnetic field lines are going like this and coming like that if you use your right hand thumb rule. So the magnetic field due to the current 2 is towards you. So that is why probably when the directions are same, the magnetic field in the middle is less, because these fields are opposite to each other. Currents are not same, that's why they are not perfectly cancelling. But yes, they are partially cancelling and you are getting a less field. But imagine if the currents were in the opposite direction, something like this, then due to this particular current, the magnetic field is still going to be inside. Hold the thumb in the direction of the current, the fingers are going inside. But for this current, hold the thumb like this, you will see the fingers are still going inside. So both the times the magnetic fields B1 and B2 are inside, so they will end up adding. That's why you are seeing probably higher magnetic field. It all starts to make sense. Correct? Okay, perfect. So let's try to figure out in the first scenario, what is my net field? B net will be B1 minus B2. I don't know who is more, who is less, but I just know they are in the middle, right? So let's just assume this as R, even this is also R. So B net in the first scenario will be B1 minus B2 because they are opposite, and B1 will be mu naught I1 divided by 2 pi R minus mu naught I2 divided by 2 pi R again. That's it. Is that right? Mu naught I by 2 pi R minus mu naught I by 2 pi R. That's all. Great. That is the first scenario. In the second scenario, the net magnetic field will be B1 plus B2. So it will be mu naught I1 divided by 2 pi R plus mu naught I2 divided by 2 pi R. Oh, great. But I know how much is this net magnetic field. It becomes 30 microtesla. Here, this same magnetic field is becoming 10 microtesla. How about dividing both of them? So if I divide 10 microtesla with 30 microtesla, guess what I will get? Okay, I don't want to sit and write this entire thing again, but visualize this. Mu naught by 2 pi R is common everywhere. Just check this out. Mu naught by 2 pi R is common, and here you have I1 minus I2. Same thing over here, guys. You have mu naught by 2 pi R as common, and here you have I1 plus I2. So when I really divide, what I'm going to get is on the top is I1 minus I2, and at the bottom I1 plus I2, because mu naught by 2 pi R and this mu naught by 2 pi R will get cancelled. Are you able to see that? I'm not doing it, but I hope you can see it. Okay, I'm not just doing that step. Alright, so this is nothing but 1 by 3 is equal to I1 minus I2 upon I1 plus I2. You can just cross multiply and still get it. This will be I1 plus I2 is equal to 3 I1 minus 3 I2. So bring that I2 over here, 3 I2 plus I2 is equal to 3I1 minus I1. So this will become 2I1 and this will become 4I2. So 2I2 divided by 2 guys will be equal to I1, and question was I1 by I2. So I1 by I2 will be 2:1. That's it. So 2:1 is the answer. Got it, everyone? Yep. Perfect. Amazing. That's all. So you just have to figure out directions. In one case, the magnetic fields were adding, one case it was subtracting. And we saw that many things were common. So when I took the ratio, it became very easy to calculate. Yeah, I could have also used component to dividend to solve the same question. But yeah, I mean, it's fine. You can just cross multiply also. It's one and the same thing. Great. Let's go to the next question on your screen. A square loop of certain side A has some current. The magnetic field at the center is how much? Okay. How much is the magnetic field at the center? This is very interesting. Let's try to figure it out. Start slowly. This is my square loop. It is carrying some current I. The side length is given to be A. Okay. We have to figure out what is the magnetic field at the center. Okay. We have to figure out what is the magnetic field at the center. If you hold your thumb like this, the thumb is going right side. Fields are coming inside the loop. Okay. So maybe the magnetic field is going to be inside. Now, what many people think is, sir, if I have a loop, so this and this will cancel, this and this will cancel, so 0. So magnetic field is 0, but 0 is not even an option. Even if it was there, don't mark it. Why is it happening? Because if you look at the top wire, current is going like this, bottom wire current is going like this. For the top wire, if you hold the thumb in the direction of the current, the field is going inside the plane of the board, correct? If you hold the thumb in the direction of the current for the bottom wire, the field again, notice how it is going inside. It is not cancelling, rather it is adding up. So this is one of the most important things for a closed figure, that the opposite sides, even though the currents are opposite, but remember, for one of the wire you are below, for the other wire you are on the top. So it ends up adding, it does not cancel. So don't even think of making the answer as 0. Great. So sir, what do I do then? How do I find the total magnetic field? I'll give you a hint. Don't take all the sides for now. Just consider one such side. Just consider one such side over here. Whatever will be the magnetic field due to one such side multiplied by 4, you will get the net magnetic field. So what am I saying? The net magnetic field will be 4 times the magnetic field due to any one such side because of symmetry and addition. All the fields will keep adding. If this is 2 Tesla, this will be also 2, 2, 2. So 4 times it will come, so 4 Tesla. Believe me, if this was a pentagon, then I would have just multiplied it by 5 because every side will contribute the same. If this was a hexagon, then I would have taken one side and multiplied it 6 times because I know each contribution will be equal and it will come 6 times for the entire figure. If this was a triangle, I would have taken one contribution and just multiplied it 3 times to find out the net field. That's all. So for all the geometries which are regular in nature, you just find the contribution due to one side and just multiply it with the number of sides. That's all. So how do I find that? Okay. So first, let's figure that out. Magnetic field due to any one such side, I will use this formula mu naught I by 4 pi r, and then I will put sine of alpha plus sine of beta. Why, sir? Because this is a finite wire, man. So for a finite wire, we have to use the finite formula. Oh, so we have seen what is the finite wire formula before. This was the one. So imagine this is one side of the square. You are finding the magnetic field here. How much is the contribution? Use this formula. Great. So let's see. How much is R? How much is alpha? How much is everything? One by one. Let's go one by one. R first. You can see R very clearly. whatever is the side length, it is exactly by 2. So R is A by 2. Next, let's figure out alpha and beta. The end point is here. The another end point is here. Both will be same, guys. Yep. This will be alpha. This will be beta. Alpha, think about it, 45 degrees. And this will be also 45 degrees. Yeah. Because this total angle will be 90 degrees. So exactly congruent. Because it's a perfect square, right? So that's it. 45 and 45 degrees. So now substitute everything. So magnetic field due to the side will be mu naught current divided by 4 pi r. We figured out the distance to be A by 2. Here we have sine 45 plus sine of 45 added together. So this will become mu naught current divided by 4 pi A by 2. I can just write it as 2 pi A. Sine 45 is 1 by root 2. Sine 45 is 1 by root 2. So 2 times. Great. This 2 and this 2 will cancel. So it will become mu naught current divided by pi A root 2. That's due to one side. We have to figure out the net magnetic field. Therefore, it will be 4 times of whatever we found out over here. So mu naught current divided by pi A root 2. None of the options are matching. Don't get worried because they have been rationalized. So this will become 4 mu naught current divided by pi A root 2 and root 2. Rationalize it. So this root 2 into root 2 will become 2. So 4 times mu naught current into root 2 divided by pi A multiplied by 2. 2 and 4 will cancel. So it will become 2 mu naught I, or we can put 2 root 2 in the start, looks good. 2 root 2 mu naught current divided by just pi A. And I think that is there as option B. Perfect. Understood? Amazing, amazing. Hi Rajdeep, good evening man. Very good Satish, very good music ethic. I am JEE. Hope you guys are solving side by side. Tushar, I'm a dropper. I studied physics 3 chapter and done PYQ up to 2002 also chemistry. Like that 3 chapter I can aim 99.2. Yes man. Tushar, many students generally start by the month of June. Dropper students I'm talking about. Some students rarely start in May. So you're not that far behind, and 99.2 percentile is easily achievable in mains. Okay, not easily, but with consistency, I mean. So don't think that it is not possible. 99.2, I'm not sure why that specific number, but even 99.5 is possible, man. Yeah. So you have good amount of time, plus you can pace it up and improve your score by the second attempt. But most likely, hopefully you will qualify and you will start preparing for advanced. Okay, great. Moving on to the next question on your screen. There is an infinitely long wire carrying current I. It is bent at a right angle. The magnetic field at a distance d on the angle bisector of from the corner is a very good question, guys. Okay, let's visualize. Angle bisector. An infinitely long wire carrying current I is bent at right angle. So this like this, this like this, but it is infinitely long. Now this was bent at a right angle. Okay, no problems. You want to figure out at a distance d on the angle bisector. Okay, so I am going to go here. This is the angle bisector. This is my distance d. Here is what I want to figure out, what the magnetic field is. Let's assume the current was going like this, So if you use your right hand thumb rule, current going like that, the fingers go inside the plane of the board at this point. So the magnetic field should be inside. That current goes up, thumb in the direction of the current. The fingers are again going inside the board at this point. If you hold this conductor like this, the fingers are going inside. If you come here, it will come outside. So again going inside, meaning they will add. So I can say whatever contribution this wire is doing here, same contribution this wire is doing here, because both of them are semi-infinite wires at the end of the day. So I can easily say that the net magnetic field at this point, the net magnetic field at that particular point is 2 times the magnetic field due to semi-infinite wires. Agree or disagree? Because both are contributing exactly the same. Okay. And plus this was at angle bisector. See, if it was not mentioned as angle bisector, if it was 30 or 60 degrees, this will be closer, this will be far. So this will contribute differently, this will be different. So I cannot say 2 times, then I will say B1 plus B2. B due to this, B due to this, I will add. But luckily, both angles are same, distances are same, so fields are also same. Alright. So what is the magnetic field due to a semi-infinite wire? We just figured it out sometime back over here. Although I told you don't remember it, but I'm just going to go back because I don't want to repeat the same steps again. It was mu naught I by 4 pi r. Think of it like this. Whatever contribution you got due to infinitely long, if you multiply it by half, that's it. It will be semi-infinite. So it will become, instead of 2, it will become 4 because 2 2s are 4. So that's exactly what you get for a semi-infinite wire. It will be half of the infinitely long wire. So you can easily say it will be 2 into mu naught multiplied by current divided by 4 pi r. Great. So this will become mu naught current by 2 pi r. But wait a minute. I do not know only what is r. You might be thinking, sir, isn't r d? No, r is not d. R is always the perpendicular distance, man. So technically, this is r. This is r. Be careful. R is always the perpendicular distance. Oh, crazy. So this is r, which is the perpendicular distance. So how much is r? Don't worry. This is same angle, this is also same angle. So this is also r, this is also r. This becomes a square. So we can clearly see r square plus r square by Pythagoras is a d square. So 2r square is d square. So we wanted r, right? So r square is d square by 2, or r is d divided by root 2. Oh, so r is hypotenuse by root 2. So just substitute that over here. So put d divided by root 2. Now root 2, if you want, you can keep it on the top. I don't know how it has been at a distance d on the angle bisector from the corner. Okay, now I'll tell you why this +1 or -1 has come, because there are 2 solutions to this. So in this case, this will just become mu naught I, and then you can just put 2 pi d, and then you can just put root 2 over here. This is the net magnetic field. Okay, this is if you take the point inside. This is if you take the point inside. But I think the diagram was not mentioned. That's why we ended up solving it like this. If it is mentioned it is angle bisector, but let's say it is on this side, then it will be a completely different answer. Okay, then it will be a completely different answer. Now coming back over here, lot of people make this mistake while solving this question. They take the magnetic field of a semi-infinite wire and they solve it and they write the answer. But let me tell you, this is not the correct answer. I deliberately did this so that you understand what is the mistake. You might be wondering, sir, why is this not the correct answer? Because this is also a semi-infinite wire only. No, sir. I thought this would be correct. See, the problem is, yes, it is a semi-infinitely long wire if you take one by one. Problem is where you are standing. You are not standing directly at the end point. Rather, you are standing at some angle with the end point. See this diagram very, very carefully. Semi-infinite wire. Because this is the most commonly done mistake by most kids for especially semi-infinite wire. Whenever you are standing exactly opposite to the endpoint. One of those endpoints. The other endpoint is at infinity. But that is not the scenario in this case. You are not standing in front of the endpoint, you are standing somewhere else. So that is why you cannot use this formula. That is why you cannot use this formula. Got it? So a lot of people end up using this, and I wanted you to see what that mistake would be. Great. So what do we do now, sir? Don't worry, man. See, the logic is still the same. The B net at this point is 2 times the magnetic field due to the semi-infinite wire. Just don't use the semi-infinite wire formula because you are not standing there. Instead, use your regular formula, which would be mu naught current divided by 4 pi r, am I right? 4 pi r, and then use sine alpha plus sine beta. That's all. So over here, 2 and 4 will cancel. You will have mu naught current divided by 2 pi. R is still same. It will be d by root 2. No doubt about it. Here, be careful. This sine alpha and sine beta, what are they? Observe carefully. One of the ends is here. The other ends is here. So technically, alpha is 90 degree. That is what alpha is. And this is beta. And beta will be 45 degrees. Yes, this is beta. This is the other endpoint. So this is the mistake. Understand? Which people ignore. So one will be sine 45. One will be sine 90. Now you will get the correct answer. So this will become mu naught I root 2 divided by 2 pi and d. Sine 90 is 1, sine 45 is 1 by root 2. Multiply root 2 inside, so you will get mu naught current. You will have root 2, root 2 will cancel, so plus 1 divided by 2 pi and d. So mu naught I by 2 pi d and root 2 plus 1, that would be the right answer, my dear warriors. Okay? Yes, that's it. That's the answer. Okay? Cool? Everyone? Pakka? Very, very good question, isn't it? Yes. Perfecto. Perfecto. Guys, try to solve this question also. This question where you have angle bisector, but the point is on this side. Okay, so try it out at home. That would be another interesting question. You have taken the point over here. Then how will you solve the question? Believe me, the answer is different. Okay, the answer is definitely different. Amazing. So let's move now to one last question before going to Ampere's law. Two infinitely long wires carrying current I are along x and y axis, the locus of points where the magnetic field is 0. Come on, everybody spam the answer in the chat box. There is one wire carrying current like this, another wire carrying current along x axis. Question is, what's the locus of the points where the magnetic field is 0? See, this wire carrying current up y axis, magnetic field will go inside over here and it will come outside on this side. That's how it will be. Right? It will go inside and come outside. Inside, go from behind, come towards you and again go inside. But if you look at this current, hold the thumb in the direction of the current, magnetic field lines are like this. So they will come outwards from here, and they will go like this. They will go down and go inside. So they will go inside like this. So there is no chance that they will cancel out in the second or the third quadrant. Because the directions are same, they will end up adding. But if they have to cancel, they will cancel either in the first or in the third quadrant. Now, because currents are the same, symmetry should be maintained. So, no doubt that the locus will be like this. Exactly, this is the locus. Because here the distance will be same. This is also r, this is also r. They will end up cancelling out each other. So, magnetic field will be 0. What is this line? X is equal to y, right? So, x is equal to y, which is option A, is the right answer, my dear. Got it? Yeah, it is not minus x. No, and it is not x is equal to minus y is equal to minus x. No, it is not like this. Okay, it would be that case maybe if the currents directions were different, but in y and x direction of currents, x is equal to y is the correct answer. Cool, Indu? Yeah. Sir, but it's 2 pi d in the previous denominator, as in? Did we miss some 2 pi somewhere here? Just let me check. This 2 and this 4 will cancel, will become 2. R will become d by root 2. Perfect, man. 2 pi d, 2 pi d. Yeah, so option D. Perfect, man. This is correct. This 2 cancelled with this 4. That's why it became 2 pi. Okay. Is that right? Hi, Pratija. Hi, Rasika Juju. Is that fine, man? Okay. Sir, I have exam on this chapter in my coaching center day after tomorrow. It's a JEE main model exam. Can you please suggest all that much learn? Whatever I am teaching, please learn it. Don't say that I will learn. There are only 2 things in this chapter: Biot-Savart's law and Ampere's law. In Biot-Savart's law, 2 things: curved wires, straight wires. That's all. Combination of them. In Ampere's law, mainly the application solenoid toroid, that is minimal, and yeah, that's all. Like force between current carrying wires. That is another major thing. Okay, now let's go to Ampere's law. Now what Ampere said is very similar to what Gauss said, but in the context of magnetism. Gauss simplified finding the electric field, which otherwise would take long time if you use Coulomb's law. Multiple charges are there, each charge will give electric field. To find that out is a complicated process. So Gauss said you find the net flux is equal to charge in by epsilon, you can find the electric field easily. So Ampere's law is very similar and it helps us find magnetic fields for certain symmetrical bodies in a much easier form rather than having to integrate. One such best example is this, which I just showed you some time back. Where did it go? Yeah, this one. See, this integration is very long. Huh? It looks easy over here right now because I have not solved it, but if you solve it, integration with limit substitution will come, r is changing, theta is changing, so many things are there. So it becomes a quite big problem. But when you use Ampere's law, right, it becomes so easy that you don't feel the pain. So what Ampere said is that if you have a current carrying wire or many wires, then you try to find the line integral of magnetic field with the for the loop. You will see it is always going to be permeability multiplied by the current enclosed. Permeability multiplied by the current enclosed. So let's understand what he actually meant. So say for example, there is a wire like this, 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 there is a wire like this. All these are random wires. You take the line integral, meaning you start from, let's say, a point and you go along a path. Doesn't matter what path you take, but come back to the same point. That is a closed path. And just like we had closed surfaces which were called as Gaussian surface, a closed path is also called as an Amperian path or Amperian loop. It's a loop, you are coming back to the same point, that's why closed loop or Amperian path. At every point you are moving, let's say this is the displacement that you have, and at every point you might experience some amount of magnetic field due to all the wires. So this is the magnetic field. You take the line integral. Line integral of magnetic field in a closed path. The line integral means integration of the magnetic field dot producted with the length that you are traveling But since it is a closed path, you put this symbol, closed line integral. That's it. That is the meaning of line integral of the magnetic field in the closed path. If you do this integration, always you will see there will be some currents which are within that loop. There are some currents which are exterior to that loop. Like this current, and this current are within that loop. But if you notice, this current I1 and this current I2, they are outside of that particular closed path. So only consider those currents which are within that particular loop, that perimeter that you have chosen. So that comes out to be equal to mu naught into the inside or enclosed currents. That's it. That is called as Ampere's law. Instead of flux, which is E dot area, here your magnetic field dot length is mu naught into the enclosed current. Got it? Yeah. Amazing, amazing. Good evening, Prithya, Durag, and yes, your stuff is coming, man. Your tool is coming very soon. Don't worry, for helping you prepare for your roadmaps, for your timings. Anytime you feel that, sir, I'm not able to study. Anytime you feel that, okay, sir, I'm not able to plan. I always procrastinate. I don't know how I'm going to do it. So don't worry. Shreyas Sir is going to help you out, stay tuned, where I will tell you how you can plan any kind of timetable, any kind of thing that you want to achieve, any goal that you want to achieve. You just make up your mind. Okay, I want to get 99 percentile. I want to get all India rank 1000. That's enough. No matter when you're starting, however your school, coaching, self-study, whatever it is, you get a plan which is personal to you, because every student is different, right? Every student has different timings, different restrictions, different study patterns, different timetables. Every student has their own way of studying, so you cannot have a same strategy applied to everyone, and something which changes on how you study. That's what is coming for all of you, so stay tuned. Yeah, okay. Great. Teacher, I don't know if this lecture even came on YouTube, but for which Indian exam? I am teaching for JEE. JEE is Joint Entrance Examination, one of the toughest examinations, not just in the country, but also in the world. Okay, so that's what it is, and this is for all the students who are in the age group of 17 to 19 years, roughly. Yeah. I'm so glad, Durag, you are loving all the theory. Now comes the critical aspect. Sir, how do I take the enclosed current? Is it just I1, I2, I3, or what is it? Okay. Before that, one important note. Just like in Gauss law, many people get confused, sir, the electric field is because of the enclosed charge or outside charge or both. The answer was both. Same way here also. Please note that this magnetic field is due to both, what both? Enclosed and outside. Enclosed and both outside currents. Keep this in mind. Both are going to contribute, but the integration of it is only dependent on the inside currents, not on all the currents. So if I ask you what is the enclosed current over here, then the answer to that is like this. Curl the fingers of your right hand in the direction of traveling the loop. So right now I'm traveling the loop like this. So curl the fingers of your right hand. Looks like some dinosaur fingers. Ignore. So this is curl along the path. Curl along the path that you are traveling. Right now I'm traveling like this. Is that right? I'm traveling like this. Okay. Your thumb, right? Your thumb automatically will point in the positive direction of the current automatically. So what happens is this particular I enclosed for the diagram that I have shown, you will notice I1 is in the direction of the thumb, I3 also in the thumb. Don't look at exact, sir, it is making an angle. No, sir. No. Like this or like that. That's all. So you will see I1 and I3 are positive. I2 is opposite. So that will be negative. So anything which is opposite to the thumb, that will be negative, guys. Is that clear? So that right hand thumb rule is coming again. So that's why I said right hand thumb rule is the most important rule. It's not the Fleming's rule or some stupid rule which you learn. Yes, Quasi, what doubt? What are the bases on which we select the loop? What are the bases on which we select the loop? Very good question. So we'll come to that also. 1 second. So our Ampere's law, first of all, it helps find magnetic field easily for symmetrical bodies, for symmetrical geometries. Number 1. Whenever you want to apply Ampere's loop law, keep 2 things in mind. Try to keep the loop such that either the magnetic field is perpendicular to that length or the magnetic field is parallel to that particular length. Because when it is perpendicular, what happens is theta is 90. So cos 90 becomes 0. Here cos 0 will become 1. So when cos 90 becomes 0, B dot dl for that part will vanish. And if it is parallel, B dot dl will become B dl. The dot product will vanish. So that is the advantage of it. Is that clear, guys? Everyone? Okay. So either try to keep the magnetic fields parallel to the length which you are traveling, or rather I will say magnetic fields you will generally know how they travel. So choose the length so that either you are traveling along the magnetic field or perpendicular to the magnetic field. That will help you find the field in a simpler manner. Okay. So let's try to solve for Ampere's loop law in the following scenarios. Look at it. Imagine there is a conducting wire which is infinitely long. Though we already know the answer, but still I am going to solve it so that you know how to apply. This has some current passing through it. I want to know what is the magnetic field at some distance r. So what I do, first I will locate that distance r. Okay bro, this is r distance where I want to find the field. I know magnetic field lines are circular due to symmetry, nothing else. So magnetic field lines will be circular in nature, something like this. This is how the magnetic field lines will look like. Okay, great. Perfect. Now what I'm going to do is, I'm going to choose a loop either parallel or perpendicular to the magnetic field. Here I feel because the loop is already present, I feel it's better for me to travel exactly along the magnetic field line. So how about me traveling along with the magnetic field? So every single time I am making myself travel parallel to the magnetic field. So my dl vector is always, in this case, parallel to the magnetic field, is always parallel to the magnetic field. So I've chosen the Amperian path in that way, that my Amperian path exactly in that way. So let's apply Ampere's loop law and see what happens. Cyclic integral B dot dl is equal to mu naught into enclosed current. Now, B and DL are parallel, that means angle is 0. So, when I split this formula or expand this dot product, it will become cos of 0 degree. Mu naught into enclosed current. The only current which is inside this loop is this current I. So, I'll just put I and nothing else, no need of any other wire. Great. Now, B is always a constant at a particular distance from the wire, no matter where you go, because of symmetry. So, I can easily shift outside the integral. I am only left with DL, cos 0 was 1, mu naught into current. Now, what is integration of DL? DL, if you go around once, you will get the circle's perimeter, circumference, which is nothing but 2 pi into R. That is mu naught into I. Therefore, my B will be mu naught current divided by 2 pi and R. This was the exact same formula for a long wire. After so much of nonsense, where is that nonsense? Let's go. See, this is that nonsense. I told you, you have to take the wire, you have to integrate it, finding the field, and then you get a generic formula. And in that generic formula, you put alpha as 90, beta as 90, solving, you get mu naught I by 2 pi. So much of nonsensical business. But Ampere's loop law helped us solve that problem in such a easy peasy lemon squeezy manner that we got it within barely few steps. Integration felt like was there, but actually is not there. So that's the irony of Gauss law and Ampere's law. The symbol of integration happens to be there, but it is of no use because most of the times the integral is either 0 or becomes very laddu integration, like this one. Integral DL is circumference. So that is the advantage. Okay, perfect. All right. No, the derivations do not come in JEE advanced exam. No, but the derivations or the understanding of how things come is important for concept, for solving this question. So, you will need to understand how things work around. You need to understand when the tricks work, when the derivations work. That is more important than the writing or the presentation of the derivation. Now, I have a very interesting thought. If there is magnetic field around this wire, is there magnetic field inside the wire? Usually we never think about the smallest of the smallest things, but what if I ask you, is there a magnetic field within the wire? Usually our wires are thin, so we never bother. But let's say we have a thick cable of current carrying wire. Inside that, is there magnetic field? The answer to that is yes, and we can figure that one out. Yep. Yes, we can figure that one out. So let's take this particular cross section of that particular cable, and inside that I want to know how much is the magnetic field. One thing I can tell you, the current will be uniformly present everywhere. The current is, let's say, uniformly present everywhere, something like this. This is the concept of current density. If you think about it, yeah, this is the concept of current density. Current is spread out uniformly on that cross section. Great. So if I happen to choose any point inside, I will probably find magnetic field lines like this, concentric circles. This is how probably the magnetic field lines are going to look like. So if I take line and from that line certain distance where I want to find how much is the magnetic field, what I will do is I'll just choose a circular path, something like this. I'll just choose a circular path, something like this. Try to visualize, guys. It's just within the cross section. It is just inside that particular cross section of that wire. This is my Amperian path. I'm just traveling like this. And as I travel, I'm traveling also in the direction of the field, because everywhere the field will be circular. Yeah, the field will be circular in nature. Amazing. So dl vector and b vector is always going to be parallel. So again, if I apply my Ampere's loop law, cyclic integral magnetic field dot dl is equal to mu naught into current enclosed. The magnetic field is parallel to dl, so b dl cos 0 will come, mu naught into enclosed current. Magnetic field is again constant, so it will go outside, so we'll just have integration of dl. But then what is enclosed current? This is the catch. A lot of people think it will be I only, but that is wrong, guys. It will not be I, and that's what I want you to realize. I'll tell you why it is not I. Look at it from the top view. If you look at it from the top view, things will be very clear. See, this is that cross section, or this is that Amperian loop or whatever I have taken over here. This was the magnetic field, and this is the exact same Amperian loop. See, the current, right? The current, right, was distributed throughout that cross section. Throughout that cross section. So the actual current enclosed here is only so much, and that, my dear, will depend on how much is the current density. So the current which is enclosed will be the current density multiplied by the area which is enclosed. Do you agree with it? How much ever area is enclosed over here into the current density, because current density is amperes per meter square. So if I multiply it with the meter squares of area, I get the current which is also enclosed. Current density, I'll figure it out, but how much is the area enclosed? This is the area I'm talking about. This is R. This is R. So that will be pi and small r square. Now, if I talk about current density, I can take the whole current and I can take the whole area. I can take the whole current and the whole area. So the total current was I and total area was pi capital R square. So what will this be? Will be I small r square by capital R square. So now I am free to put that I small r square by capital R square. So this will be mu naught current into small r square by capital R square. Integrating dl, you are just going to get 2 pi small r mu naught current small r square by capital R square. R cancels, so you will get mu b is equal to mu naught I. R has got cancelled, and what I am left with is 2 pi r square. Now, should I remember it? Of course, please remember this formula. Mu naught I by 2 pi into capital R square, and small r remains over here. But this is the field inside the wire. This was the field outside the wire. So if I combine both of them, the magnetic field inside the wire will be mu naught I divided by 2 pi r square into small r. Magnetic field outside the wire is mu naught I divided by 2 pi r. So this formula is when r is less than r. This is when r is more than equal to r. So we can now see the difference in the formulas, and we can also draw a graph like how we used to do in electricity. This is magnetic field, this is distance, this is 0. This graph came so many times, man. What can I say? Inside it is proportional to r, so it will be a straight line. Outside it is inversely proportional to r, so it will be a rectangular hyperbola. And this shift happens exactly at the boundary, and it is maximum on the boundary. So initially it is obviously proportional to r, later on it is inversely proportional to r. So this is what you can see. Got it, everybody? Clear till this point? So we have used Ampere's law to figure out literally everything. Okay. Oh, is it? South Korea is very different? Crazy, man. You know, the funny thing, man, I don't know, I can't read your name, sorry. Maybe you can type it out in English. We are very fond of South Korean shows and we watch it paid. So, I don't know how it is for you guys out there. Maybe, obviously, if it is on Netflix or some Amazon Prime or something, maybe it is paid. But we are really fond of your Korean shows out here. And maybe the reason is we are bored of the content which is being created, you know, over here. And we really love your shows. So I'm so glad that you guys are finding out our education content to be very interesting. And I'm so glad that you found this channel. Thank you so much, man. Yeah. Thank you, Shadow. Yeah. Great. Right. Now, let's do some questions coming up on your screen, starting one with this. Steady current I flows in an infinitely long, hollow, not solid, hollow conductor, radius r. This cylinder is placed coaxially inside an infinite solenoid of 2r, the magnetic field at a distance r from the axis. Okay, great. Let's see what you can answer. Now, but for this, magnetic field at a distance r. Actually, I'll tell you how to visualize this question. There is a infinitely long hollow cylindrical conductor. So this is my hollow cylindrical conductor, and there is another solenoid or hollow. Solenoid is basically a hollow cylinder only. So don't get confused, sir. I have not learned solenoid. It's nothing but a hollow cylinder only, man. Okay, this is your other cylinder. Now, this is 2r. This thing is basically 2r, and this thing that you see over here, that, my dear, is basically r. You are at a distance r which is less than 2r but more than r. Okay, that means you are somewhere over here. That is that r. So question is, what is the magnetic field at that distance? Don't worry. Oh, trust me, the plus point of this channel is not just that we are teaching in English, but we are also delivering the best content, whatever they get in the usual stuff. Plus, there are a lot of students in our country who just understand, you know, apart from their mother tongue, of course, like Tamil or Telugu or Kannada and, you know, Tulu or maybe Marathi or whatever, they understand English. So, a lot of kids are there, and that was the whole purpose of this channel, and that's what I've been doing for quite some time. Okay, I'll tell you, you can use Ampere's loop law, man, and you will realize that you just have to go around once, and the enclosed current will be only the orange one, not the yellow one. That's all. So, are the currents same? Okay, same currents, let's assume. So, there is a current I, and there is also that yellow thing is carrying some current I. But that yellow current is basically that outside current. It's outside the loop Amperian path. So don't even consider. But it's the only inside current which will matter. So even if you do integral B dot dl is equal to mu naught into I enclosed. So I enclosed will be just I. This will be B outside, integration of dl. So integration of dl will be 2 pi r. That's it. So you will get B is equal to mu naught current divided by 2 pi r. It's Ampere's loop laws application, nothing else. So mu naught I by 2 pi r, which is obviously option B. That is the correct answer. Okay, the outside one didn't matter. I don't know whether it reminds you of electrostatics where we had shell problems. Do you remember that? There was a shell inside a shell, and when you are somewhere in between that space of those shells, it's the inner shell's field which matters. The outer shell has zero contribution because when you're inside a shell, the electric field was zero. So the shell now has converted to a cylinder for magnetism, because you don't get spheres for magnetism. Here you get cylinders carrying current like that. So when you are inside a cylinder, the magnetic field is 0, and when you are outside a cylinder, the magnetic field is just like a straight wire. mu naught I by 2 pi r, that's it. Same like shell theorem, same like electric fields for a shell. It's exactly same. Instead of a sphere, now you have a cylinder. That's the only difference. And why not? I mean, look at it. Even Gauss's law was applied for an area, but in magnetism, it's applied for a length. Similar law, mu naught I enclosed, but you are integrating with respect to length. So if things are moving from areas to lengths, so why not a sphere becomes a cylinder? So probably that's the reason. Okay. Let's see whether you can solve this. A long straight wire carries some current I, uniformly distributed on the cross section. The magnetic field at a distance. Oh, this is very direct, man. Magnetic field at a distance R from the center, and assuming this is R. So what is the magnetic field inside? I just told you is proportional to R inside, because the graph is a straight line. But the moment you shift to outside, that's when it becomes inversely proportional to R. But for us right now, we are inside, so it should be proportional to R. That's the answer, option B. Perfect. Great. Amazing. Yes, Bharat, mobile phones, TVs, satellite signals do use electromagnetic waves. Definitely. Moni Sharma, welcome, man. And you are a class 9 student, and let me tell you, let me warn you, if you are a class 9 student, very, very important, a big, big warning. Once you start watching these classes from 9th standard, you become addicted and you become regular, and you feel like completing the syllabus by 10th standard only. So the side effect of this is usually you end up cracking the JEE exam with an all India rank less than 1000. And I am telling this to you with experience, because this is what I have seen. Students who were generally associated with me from 9th standard or 10th standard, it's not like I was teaching them JEE stuff. Some students watching me on YouTube, some students watching me or listening to me offline when I used to teach offline. I used to teach foundation. So they end up loving physics, they end up loving maths, they end up thinking, they end up analyzing, visualizing, and I don't know what happened to all these kids. I never thought that, you know, I used to be like, okay, fun and jolly to all these kids, and suddenly they become like all India rank 14, 17, 20, 30. So, you know, that's the kind of ranks that these kids crack, and I'm pretty sure if you are motivated enough, you will too crack it, man. Hi, Kaur. Oh, Anusurya, I hope you are loving the classes, by the way. Okay. So, like you can see, I'm going everything in detail. I'm going everything conceptually. For those students who are wondering, sir, I want to solve more questions. I want you to take more questions. I understand your concern, but please understand, we need to have two kinds of lectures. You can't have a single class which just does problems also, concept also, from the scratch also. I will take you to advanced. See, some teachers will tell you that I am going to teach you from the basics and I will take you to the moon. I will take you to the advanced. I will take you outside solar system. I will take you to outer galaxy only. I don't know how it is possible. See, the point is not to cover the syllabus, okay, rather it is to uncover the syllabus. And there is a big difference between covering the syllabus and uncovering the syllabus. And if you were there at the start of today's lecture, you would have noticed how I told you what magnetic field was. And it is way different than, I think, 99.9999% of any of the classes, forget YouTube even paid. Yeah? Okay, cool. Let's move to the next concept of solenoid and toroid. Have you built an electromagnet ever? Thank you, Kaushik, for all the love, man. Means a lot. Means a lot. Electromagnet. You take a nail, you put some coil around it, and connect that coil to a battery. Current flows, and immediately it starts attracting magnetic objects, iron, other magnets, anything. That's an electromagnet, and that's what a solenoid is at the end of the day. The use of this is in many places. One of such example is a shipping yard. You would have seen those big containers in which a lot of stuff, your goods will go in ships, in trains, in buses, sorry, not buses, trucks. So these containers need to be lifted, taken, put down, so many activities. So they don't generally use hooks because it's a very time consuming process to hook it, again unhook it, and it's very flimsy. Instead, what they do, these containers are metallic, magnetic in nature, meaning they get attracted to magnets. So what happens is you have a big solenoid like structure where current will pass. It will behave like an electromagnet when current is passed, and it will attract that container. Now that container is stuck to that, it will move easily, and then wherever you have to let it go, you just keep it and then turn off the current. The magnetism goes, easily you can pluck it out. So don't get scared. I know you are thinking, sir, won't that container fall? You are just believing electricity and magnetism. Yes, man, the world is based on beliefs. So here we are believing that the current is going to produce a good magnetic effect and thereby attract that container. So that's what exactly happens. Cool? Anyways, now what is a solenoid? Solenoid is basically you take a cylinder and you wind a coil across it. How is this different from a coil with n number of windings? That's a brilliant distinction that you should know, because a lot of people think, sir, if I take a coil and if I might do it multiple times, isn't this the same as this? The answer is no. See, when you take a coil and have n number of windings, the formula for that mu naught I by 2r and into n. This is different from this because here all the coils, all the turns are in the same plane. Here this turn is in different plane, this, all are in different planes. So it's different, man, different planes. So the magnetic field's strength, behavior will be also different. In fact, if you see, if I just place a single coil, the magnetic field due to that coil will just come like this and it will go. Will just come like this and it will go like that, isn't it? But imagine now there are multiple coils placed besides each other, same current is passing. Then what happens is, it feels as if you have taken a coil and you have stretched it. So whatever was happening in this plane has now got elongated, got stretched. Yes, the magnetic field is still going and coming out, that's okay, but you know, the magnetic field looks almost parallel, almost stretched inside that long cylinder. It's as if you have taken the coil and stretched it. So that is what a solenoid is. And of course, it's different from a coil with n number of turns. If you take the coil of the solenoid, you will notice that the field will be produced in a particular manner. It will come out from one side. That side will call it as north. It will enter inside. Wherever it enters, we'll call it as south. But inside the solenoid, it will travel from south to north. I think the directions are, why are the directions wrong here? Yeah, it will travel from south to north. It will travel from south to north. That's how they travel, man. That's how they travel. So outside, it's like a bar magnet, north and south pole. It comes out from north, goes inside and continues inside. Circular loops. What is very important is inside the solenoid, inside a long solenoid, it's almost constant, meaning it is basically uniform. It is basically uniform. Outside, if you go, the fields are very far away. So the magnetic fields outside, magnetic field outside, they are so far away that you hardly sense it. It is negligible or it is basically zero. Cool? So that is something which you should know. Inside it is roughly uniform. You can see parallel lines. Outside it is negligible. The field lines just go really far away. Very weak. and inside again it comes back. How much is that magnetic field? Let's just calculate that very quickly. It's not that difficult. You can take a cross section of the solenoid. This is the cross section of the solenoid. It's like I'm cutting the cylinder into half. I'm cutting the cylinder into half. So visualize that now. Yeah, I want you to visualize that cut which I have made. Okay, so maybe you might see currents coming out from here. These are different windings. Each dot represents a wire. That wire will go again inside. So cross means that same wire is going inside, just like the vector notation. Crosses are going inside, dots are always going to come outside of the plane of the board. Now inside of it you have magnetic field lines which are almost going to be parallel and uniform, something like this, something like this. This is the magnetic field. I am interested in figuring out how much is this magnetic field. So I need to choose an Amperian path very carefully. And I know some tactics. One is choose a path where the lengths are parallel or they are perpendicular. So how do I make it? If I go parallel, I will go to infinity, man. And when do I come back? I need to return also. Okay, so I need to return. So can I go circular? If I go circular, everywhere the field will be 0 like this. So it doesn't make sense. Sorry, not field will be 0. B dot dl will be 0 because magnetic field is that way. Length is perpendicular. No, doesn't make sense. So another possible way is if I go maybe partially inside, go outside. So can you do that? Why not? Any path I can take, man. Doesn't matter. You cannot restrict me. But it has to work conveniently, easily. So why not going like this? Just choose a path like this. I think it will be helpful. Go like this, go like that, go like this, go like this. This is my path, closed path. And best part about this, outside I already know the magnetic field is 0 outside. So when I apply my Amperian loop law, B dot dl is equal to mu naught into I enclosed. This integral will now split into multiple parts. Part 1, part 2, part 3 and part 4. So integral B dot dl in part 1 plus integral in part 2 B dot dl plus integral B dot dl in part 3 plus integral B dot dl in part 4. Basically cyclic means complete, right? So I'm splitting that entire cycle into 4 parts. Mu naught into I enclosed. Okay. Now observe. In the first part, magnetic field, this one and dl are in the same direction. So angle is 0. So this will become B outside integral dl for the first case. For the second case, magnetic field is perpendicular. So B dot dl will be 0. So the second term will be 0 because angle is 90 degree. The moment you go outside, magnetic field only is not there. So when you multiply 0 with any number, the answer is 0. So number 3 integral will be 0. When you come back here, magnetic field, length and magnetic field are perpendicular. So cos 90 will be 0 because dot product means cos. So 0 is equal to mu naught multiplied by enclosed current. Oh, nice. So I have B dl. So this length, if I call it L, so it will be just B multiplied by L. Integration of dl in this first path. dl. Integration in this first path is the length of this rectangular path. Great. Is equal to mu naught multiplied by I enclosed. Now let's tackle how much is this I enclosed. If you see carefully, you will realize the enclosed current is only this much. Oh, yes, sir. Absolutely right. So how much will this current be? Oh, there will be some wires. Each wire is carrying current I. So I will be there some number of times. right? So what if I already knew a term called as how much is the number of turns per unit length? How many number of turns are there per unit length, which is total turns by the total length. Here total length could be anything, total turns could be anything, but that symbol I will call it as small n. Small n is how many turns, windings are there per meter. If I have a solenoid with 1000 turns in 2 meters, that means per meter it has 500 turns. So small n will be 1000 by 2, which is 500 turns per unit length, which is per meter. Okay, if that is the case, then this current enclosed, my dear, will be, current I will be there, but multiplied by number of times it is coming inside this particular area. How many times will it come? The number of turns per unit length multiplied by the length. Is that right? Per meter, how many turns are there into the number of meters will give me total number of wires times the current is entering or exiting. That's it. So if it is INL, so instead of I enclosed, it makes sense to just put I, N and L. Hence this L and this L just got cancelled and we are getting it as mu naught N I. Now please remember this formula. Magnetic field inside is mu naught Ni and it is a constant. It is not dependent on any distance like R or anything. Yeah. Hi Asuka Langley, welcome man. Awesome. Oh, Vinay, we just discussed that last time also. Yeah. Great. Okay. Great. Amazing. Now, there is one more important formula which you should know. In fact, instead of blocking this, I will block it later on here. So if we have a solenoid and this is the magnetic field lines. When you are in a region where the lines are basically parallel to each other, basically deep inside, so magnetic field inside where the lines are parallel is mu naught Ni, and it is obviously uniform magnetic field very much inside. This formula we just derived it. Magnetic field when you are completely outside the solenoid is negligible. We just said it is going to be 0. But another important formula which you should know is what happens when you are at the end here or even here. How much is the magnetic field at the end? So that particular magnetic field at the end of the solenoid is very similar to this mu naught Ni, just that you have to divide it by 2. So exactly half of whatever you get it inside. Now this formula comes very rarely, but if it comes, you know how to use it. So whatever is there inside, exactly half of it. Outside, it completely vanishes. Okay? Clear? So remember this. All right. Sir, why can't we just take number of turns? Yes, you can. Exactly, that's what you wanted only, man. Who is asking that? Rasik Aju. Okay, perfect. So let me tell you. Over here, we exactly wanted into number of turns. But how do I know how many turns are there inside this part? Usually I will know the number of turns in the total solenoid, correct? But here, this is not total solenoid. The solenoid is much longer. So that's why I have no other option but to take the number of turns as the number of turns per unit length multiplied by the length. Does that make sense? So that is the reason behind it. Now, if you take a solenoid and give it to a very strong person and you ask that person, man, your job is bend that solenoid, and he takes it, bends it and connects it. So these two open ends are now connected to each other. Are you able to visualize it? It's a tube now. That, my dear, is nothing but a toroid. That's a toroid. It's a solenoid which has been bent and connected. So, what is the difference? Nothing. It's the same thing, nothing else. So, earlier what used to happen, those open ends used to be there. So, through which the field lines used to escape out in a solenoid. So, if you remember, in a solenoid, the field lines used to escape from the open ends like this diagram. They used to escape. But if you join these, they will never escape. So, what happens is the magnetic field is now trapped inside the toroid. It does not go outside an ideal toroid. So, here it's not an approximation anymore. Rather, it's an exact thing. The magnetic field outside is exactly zero. Very, very important. In solenoid, it was approximately zero. Remember that? Because outside fields were there. It was so small because they spread out so widely till infinity in a big space. So that's why it was approximately zero. There is a difference. Here it is exactly zero because it do not escape only. So now the only thing is, what about the field inside? It's the same, man. It's a solenoid, no? If it is a solenoid, what's the magnetic field? Mu naught Ni. So the magnetic field inside is still going to be the same. So the magnetic field is there only inside. It's going to look uniform and it will be mu naught N into I. But there is another way of writing this small n now. There is another way of writing this small n. Yeah, think about it. Sir, will n be equal to 1 by 2 pi r by 1 by number of turns per unit length? In some question, finite solenoid. See, if it is not a very, very long solenoid, even if it is a finite solenoid, usually you are given the number of turns and the number of meters there are. So, from that you can get it. Achha, you are talking about the length of the wire. But length of the wire, even if it is given, you need to know the spacing between the wires and all of that. So, I'm not really sure why you wrote that 1 by 2 pi r formula. I don't think that is the right one. So, Vinay Shiva Kumar, just recorrect it. Okay, you are usually given N and you are given L. What you are talking about is this toroid formula, I think. Okay, so this number of turns per unit length, the total length of the toroid. What is the length of a toroid, guys? What is the length of a toroid? Think about it. The toroid will have some radius, no? I will call it R. So it will be 2 pi r. So the number of turns which are actually there will be, let's say, capital N, and the total length will be 2 pi r. So this is the formula for a toroid which you usually use. Total turns are given and the radius of the toroid is given. This formula. Okay. So I guess Sivakumar, you are asking about this formula, not for a solenoid. Okay. Clear, everyone? Very good, amazing, proud of you. Let's solve some questions, man. And here it comes, the first one on your screen. Here it is. A long solenoid has 200 turns and carries some current I. Magnetic field at the center is 6.28. Another solenoid has 100 turns per centimeter. Okay. The current is I by 3. What is the magnetic field at its center? Okay. So basically we have to use this formula. Magnetic field is mu naught into N into I. Turns per length is given, current is given. So we all can see magnetic field is proportional to N and I also. So if I write B2 by B1, it will be N2 by N1 into I2 by N1. So the second time the magnetic field, I do not know actually. First time the magnetic field 6.28. So put number 6.28 into 10 raised to minus 2. Now if you are wondering what is this Weber per meter square, well, it is actually Tesla only. So a Tesla is also Weber per meter square. That's a different way of writing. Like how you can write kg meter per second as Newton into second for impulse. So same thing. Alright. So Weber is actually the unit of flux, which you will learn later. Anyways, coming back now over here, B2 by B1 is done. N2 by N1. What is N2? Number of turns in the second scenario is 100. In the first scenario, my dear friend, it is going to be 200. What is the first current and the second current? The second current is I by 3. Okay, so put I by 3. The first current was just I, my dear. All right, so this will be 1 by 2. This will be just 1 by 3. And this will be just B2. And this will be 6.28 into 10 to the power minus 2. So just shift it on the top and you will get the answer. So B2 will be 6.28, 2 3s are 6 into 10 to the power minus 2. So this will be 1.05 into 10 to the power minus 2, because this will be approximately 1, no? So 1.05 into 10 to the power minus 2 Weber per meter square, which is also a Tesla. Perfect. So just based on simple formulas. Let's do a question on toroid now. A toroid has a core of inner radius 25, outer radius 26, around which 3500 turns of a wire are wound. If the current is 11 amperes, the magnetic field inside the core of the toroid is. So what does this question mean? This is something like this. What they have told is, see man, this is 25, this is 26. There are 3500 turns, current is given. So figure out the magnetic field. Now when I write the magnetic field of a toroid, it is still mu naught Ni, but the number of turns per unit length becomes total turns by total circumference, 2 pi r. Now what is this r? Is it 25 or is it 26? It's neither of them, it is somewhere exactly in between. So this r is actually 25 plus 26 by 2, which means it is 25.5 centimeters, which is 25.5 into 10 to the power minus 2 meters. So it is the average of that. So when I mentioned the word radius over here, right? So don't think it is inner radius, it is actually the average radius of the inner part and the outer part. So it will be somewhere over here. Okay, it will be somewhere over here. Great. So just put all those values and you will get the answer, man. Nothing else. So mu naught is 4 pi into 10 to the power minus 7. You have 2 pi over here. Radius is this, which is 25.5 into 10 to the power negative 2. Number of turns is 3500, and current is 11. Okay, that's it. So solve this and you will get the answer as 3 into 10 to the power minus 2. Okay, so solve this, you will get it as 3 into 10 to the power minus 2 Tesla. Cool, everyone? Perfect. Very good. Amazing. So that's how the questions are of basically solenoid and toroid. Usually you don't get very complex questions of solenoid, toroid. You will see most of the JEE advanced questions are based on Biot-Savart's law and very little on Ampere's law. Okay, that's what you will notice. But yes, the next part, whatever I'm going to teach, that will come. So current carrying sheet and force between current of wires. Okay. Now this particular arrangement where, observe this. This is a sheet, and this sheet has lots and lots of wires parallel to it, arranged like this. They are entering from here and exiting from there. So this is a sheet of wire carrying currents, just like you had charged sheet in electrostatics. If a single wire creates a magnetic field something like this around it, when you place multiple wires parallel to each other, what happens? They all produce magnetic fields, and it's a large sheet, large number of wires densely packed. Then the magnetic field is no longer circular just like that, because then they will intersect. That can't happen. So what you end up seeing is the magnetic field lines go like this, turn and come back like this. This is how you will see the magnetic field lines. So they will probably go like that, come like this, go like this, turn like that, come like this, and come like that. Go like this, turn like that, like this, and like this. This is what you are going to see. We are not worried about the end effects. So at the end, right, whatever you are seeing over here and over here, these two places I'm not worried about so much right now. I'm not interested also. These end effects, they are called as fringe effects. That is called as fringing. Fringe means end, fringe effects. That word fringe means that's a fringe outfit. That means it's an outfit which is like towards the end. It's like nobody knows. It's somewhere on the edge. So something like that. It's a fringe effect. So it's at the end. So we are not worried about the end. We are going to be comfortably placed somewhere inside or within that sheet. It's a large sheet and you are somewhere in the middle. So what you will see anywhere in this particular region, is that the field is uniform. Yes, the magnetic field is uniform. That's all. And this field is very easy to calculate. Oh, by the way, direction, use your right hand rule. Huh? Again, current is going up. See how the fingers are going, curled fingers going like that. Exactly following right hand thumb rule, nothing different. Yeah, all right. Now, getting knowledge about physics, start loving it because of me. Thank you. I'm so glad. Who is this? Satish Das. So good. I'm so glad, man. Now, if you ask me what the formula is, I'll tell you it is very similar to what you got in electrostatics. For a charge sheet, what did you get? Sigma by 2 epsilon naught. So I have a feeling we'll get very similar formula. That 2 will be there, but instead of permittivity, what will we get? Permeability. But permittivity is below, so permeability will be on the top. How do you know that, sir? Just remember Biot-Savart's law. How did it look like? Mu naught by 4 pi. In electrostatics, 1 by 4 pi epsilon. Epsilon was below in electrostatics. In magnetism, mu naught went on the top. So I think in magnetism, everything is opposite. So for permittivity and permeability. So if permittivity is below, so permeability will be on the top. So you'll have mu naught on the top. Oh, great. Sigma is there. It was charge per unit area. We also noticed when we moved from electrostatics to magnetism, area becomes length, or length, if it is there, it becomes area. So instead of charge per unit area, maybe it might become current per unit, not area, per unit length. And it makes sense because what will happen is, if you take 1 meter of this sheet, how much current is there? So that current per unit area is called lambda. Current per unit area. Amperes, sorry, not area, again I wrote area. Current per unit length, my bad. Current per unit length is basically lambda. So here what I write is lambda, my dear. Okay, so this becomes the formula for your current carrying sheet. What's the magnetic field like? Very similar to sigma by 2 epsilon. 2 was there still, epsilon became mu naught, but on the top, charge per unit area became current per unit length. And it means for this sheet, if you take a meter length, how much amperes is passing in that length? If more arrows are there, more current. Less arrows are there, less current per meter. Okay? Alright. So, here, whenever you have a current sheet, think of it like this. If you look at it from the top view, you just have a single wire versus 2 wires versus, let's say, 3 wires versus, let's say, multiple wires. When you have one single wire, the magnetic field lines are like this. When you have 2 wires, then the magnetic field lines are like this. When you have 3, they go like this. This is how it is. And when you have like this, many of them, so what happens is barely it goes inside, it will just go like this and it will come around like this. This is the top view, guys. Don't you see here it is almost uniform field. These are many wires arranged together, inside out, inside out. So now you view it in 3 dimension. It is exactly this. So this was the top view. So the magnetic field lines here is almost uniform. At the ends, I'm not interested. Okay. And what parameter I need is basically this. If I take 1 meter, how much current is there? So current per unit length is called lambda. How much current is there per meter? So that helps me figure out the magnetic field. Mu naught lambda by 2. You can also get it via Ampere's law. I leave it up to you now. Is that okay, Raj Dubey? Perfect. Yeah. Now is it clear, Kaur? And how to get the direction? Use right hand thumb rule, man. Nothing else. So the current is coming towards you. Thumb is in the current. Fingers will curl in the direction of the magnetic field. Simple. So it basically comes from single wire to double wire to triple to 4. If you just start using mathematical induction kind of a principle, you immediately understand why the field lines are like this. For 1 wire it is circular, for 2 wires it's almost circular but it bends like this. 3 it is a wavy thing. For many such wires it's almost wavy but almost flat also. So it almost becomes uniform. That's what it is. Okay, so that's what a current sheet is all about. Now let's go to the last part of this chapter, and that is the force between current carrying wires. If there are 2 wires which are carrying current, yeah, okay, come on, guys, focus. Core and this, who is this? Cricket lovers, man, who are you, waste fellows, coming here to flood? So force between current carrying wires. If you have 2 wires carrying currents, then they can apply forces on each other. How, sir? Let's understand. Let's take the situation where you have a wire like this carrying some current, let's say I1. We all know it will create a magnetic field around it like this. So on this side it will come towards you, on this side it will obviously go inside the plane. Now we place another wire beside it. Let's say that wire is carrying current like this, or maybe carrying current like this. Whatever current the second wire is carrying, I will call it as I2 over here. There might be some separation between these 2 wires, and that particular separation or distance I will just call it as D, nothing else. Now we know whenever a magnetic field passes through a current carrying wire, it experiences force, and that's what we are going to do. If you look at this scenario, when the currents are in the same direction, magnetic field is inside, current is here. use the concept of IL cross B, which we learnt last lecture. Length is always in the direction of current. Magnetic field is inside. Length cross B. Oh my God, thumb is coming this way. So the force on this wire is like this. Obviously, this force is attractive in nature. It is attracting this wire. If you do the same thing for this wire, meaning this wire will create its own magnetic field. How will that magnetic field apply the force? It will be exactly this way. So even if you solve it, it will come out to be like that. If you do, when the currents are opposite, length is down, magnetic field is inside, length cross B, length B cross, force is coming that way. Amazing. This force is always taking it away, so it is repulsive in nature. So the same thing will be over here also. So it is attractive when the currents are same. Look at it, exactly opposite to electrostatics. If you have two positive charges, they would repel. But here, currents in the same direction, they attract. When you had positive and negative, they would attract. Here, opposite currents are repelling. So it's exactly opposite, guys. How much is this value? It's not difficult to find it out. So if you figure out first how much is the magnetic field at this location, it will be mu naught into current divided by 2 pi into d. Distance I know, current I know. At this point, long wire, it is mu naught I by 2 pi r. R is d, current is I1. For the force, I will need current on which the force is acting into the length into the magnetic field. So I2 is there, L is there, B is nothing but mu naught I1 by 2 pi and d. Bring that length term below. So it will become force by length is equal to mu naught I1 I2 divided by 2 pi and d. Now this formula is very important. It gives me the magnitude of force acting per unit length between two parallel or anti-parallel wires. Mu naught I1 I2 by 2 pi d. Mu naught I1 I2 by 2 pi d. So to summarize over here, currents in the same directions will attract, currents in the opposite directions will repel, and the magnitude of these forces are given by per unit length mu naught I1 I2 by 2 pi into the distance between them. This is what you should remember. Okay, cool. Shall we now do some questions on this? Yeah, this is the last part of it. This is the last part of it. Ready, my dear warriors? Okay. Let's do questions on it. First question on your screen, here it is. Two parallel wires are there, long, separated by some distance, carrying current I1 and 3I. The force per unit length is how much? Okay, direct substitution just to check how well you remember it. So the force acting per unit length, I just told you mu naught I1 I2 by 2 pi and d. So mu naught is as it is, current is I, and next one is 3I divided by 2 pi d. So it will become 3 by 2 mu naught and then pi and then I square and then d. 3 mu naught I square by 2 pi d. They are parallel wires. If they are parallel, that means same, that means they will attract. Yes, they will attract each other. Hence, the answer is basically option A. Else, it could have been repulsive also, right? But they are parallel. Anti-parallel means opposite. And they would have repelled. Yes, so they will attract. Option A. Let's go to the next question on your screen. Three long wires, parallel, I, 2I and 3I, separated by equal distance between adjacent wires. The force on the middle wire of length L is 3 long and parallel. Okay, interesting. So we have one wire like this, another wire like this, another wire like this. What are the currents? I, 2I and 3I. Okay. Equal distance d between them. This is also d, this is also d. Now we all know when the wires are parallel, they will end up attracting each other. Same currents attract. So the force on the middle wire. So I and 2I will attract. I and 2I will attract. 2I and 3I will also attract, no? So 2I and 3I will also attract. But the question is, what is the force on the middle wire? Notice 2I is getting pulled here also and here also. The net force will be the subtraction of these two forces. Great. So I can immediately say the force on that middle wire per unit length is nothing but this force minus this force. Two forces are there and minus it. So the first one will be mu naught I1 I2, meaning I into 2I divided by 2 pi d, and the next one this and this. So mu naught 2I 3I divided by 2 pi d. Whatever answer you get, we will just put it inside the modulus because I did not know who is big or who is small. So notice how mu naught I square by 2 pi d will be common. Modulus is there. Here the number 2 is there. Here the number 6 is there. 2 3s are 6. 2 minus 6 minus 4. Mod is 4. So mu naught I square by 2 pi d multiplied by 4. 4 and 2 cancel. So mu naught I square by, no, 2 is also there, and by pi and d. So that's the force acting on that length. So mu naught I 2 square. Yes, mu naught I 2 square. Where is that 2 square? 2 square. This one, guys. That 4 by 2 they have not cancelled. That's all. Otherwise, that is the answer. Okay, 4 by 2 they have not cancelled as 2, but here we had cancelled it. That's all. Answer is B. Cool. Very good. Let's do one more question coming up on your screen. A rectangular loop of side A and B carrying currents I2 is placed near a long wire I1. The straight wire is parallel to the side A and is at a distance C from it. The net force on the loop. Very good question. We have a long wire like this, and then we have a rectangular loop like this. The rectangular loop AB carrying current I2. Okay, this is carrying current I2. This long wire is carrying current I1. The straight wire is parallel to the side A and is at a distance C from it. So this distance, my dear, is C, and this is A and this is B. Okay, perfect. Great. What is the net force on the loop? Very good question. First of all, realize that the magnetic field due to that long wire will be circular and it will not be uniform throughout the length. So here it will go inside, it will be very, very strong, and as you go far away, the field reduces. Here it will be very, very strong. So the magnetic field strength is strong, weak, weaker, weakest. If you consider this part of the wire, you will notice the current is going that way. If you want, I'll show it. Here the current is going this way. So if you use IL cross B formula, L is that way, magnetic field is inside, force will come out to be this way. I'll call it F0. If you consider this wire, same magnetic field will create a force like this. Now these two, F0 and F0, will end up cancelling out each other. F0 and F0 are cancelling out each other. So don't worry about them. So focus your complete attention on this part and this part. Out of them, you will realize that this wire and this wire are parallel to each other. So that's why this part should experience a force like this. I will call it as F1. This F1, no doubt, will be mu naught I1 I2 divided by 2 pi distance, which is C. This wire and this wire, the currents are opposite, so they will repel. opposites will repel, correct? So the force will be like this. I will call it F2. Now this F2 will be mu naught I1 I2 but divided by 2 pi C plus B, total distance C plus B, that's all. But these forces are always force per unit length, so force by A and force by A, force per unit length. So what is the net force on the loop? So if you want to find the net force on the loop, it is just F1 and F2 subtraction. So F will be F1 minus F2, guys. So F1 is this mu naught I1 I2 A divided by 2 pi C. F2 is nothing but mu naught I1 I2 A divided by 2 pi C plus B. A lot of things become cancel, common. Mu naught I1 I2 A is also there, 2 pi is also there, and here we'll have 1 by C minus 1 by C plus B. 1 by C minus 1 by C plus B. And which direction will it be? F1 will be strong, F2 will be weak. So the net force will be left side, will be towards the wire. That's the answer, towards the wire. So how do you know this is strong? Think, man. Here, this is going to be strong because the field is also strong, no, here. And as you go far away, that's how the field becomes weak. So that is why the force here is smaller, here the force is larger. So the dominating force will be the left force as compared to the light force. Hence, the left side will be dominating. That's why I know it will be towards the wire. Isn't it a good question, guys? Yeah, brilliant question. Many people will get confused what to do about these two segments, but those two segments didn't even matter. They got cancelled anyways. So don't worry about it. These were the two segments which you had to solve it. Okay. So that was the last question and we have completed this chapter. Why is it F1 minus F2? It is F1 minus F2 because they are opposite. These two wires are same direction, so they will attract. These two wires are opposite, so they will repel. So F1 is here, F2 is here. So on this entire loop, net force will be F1 minus F2, opposite directions. Is that okay now? Great. I hope Jian, Muskan, it's clear. I'm so glad, Satish, you guys enjoyed. Next Friday, let's do electromagnetic induction. Okay? Let's do electromagnetic induction. We are focusing right now on part 1 of, you can say NCERT, but it's not exactly NCERT also that we are following. So, you know, we'll continue with that. So, electromagnetic induction, and hopefully after that, then we'll do EM waves or maybe AC. Yeah, we'll see how it goes. Okay. All the best. Take care. Keep studying. And I want to see all the comments for the homework question. Where is the homework? I gave it to you in the middle of the class, so you figure it out. Okay. So, I want to see how much of attentiveness was there during the class. So, I given a small homework, solve it and paste the answer as comment section. Thank you. Bye bye. Take care. Have a great time.